Okay.
Good morning, everyone. Welcome back to day 3 of GIAN course on adsorption techniques for carbon dioxide capture, modeling, and simulation insights. So, today we have two lectures in the morning, lecture 8 and 9 by Dr. Debanshu. He will be talking about flow through packet beds and also adsorption separation by continuous systems. He will introduce the pressure swing adsorption. In the afternoon, there is one lecture on modeling of adsorption processes that is followed by tutorial 2 on estimation of the adsorption parameters, which is followed by research seminar uh, from Dr. Debanshu. Yeah, please
Okay.
continue.
Yep. Thank you. Thank you. Okay. All right. Okay. Welcome back, everybody. So today we'll be first talking about the flow through the packed bed, dynamics of the absorption column, and PSA, TSA, and VSA. Okay. So we'll see what are these, right? So first is that one of the big thing is that when you try to design a adsorption column or any bed, there are a couple of things that you really need to consider. One is the surface area. So when you look into a particular adsorbent, the adsorbent itself has got or provide you the surface area that you need for the adsorption to take place. However, one of the important thing there is that when the gas flows through it, does the gas has the access to the surface area? So I think that is one of the biggest thing in the design of the contactor that which we really need to have, because without the surface area available there, the adsorption cannot effectively take place. So these are the different beds that actually gives you different type of surface area. We are mainly be focusing on to the packed bed. So I have a plan that on the final day, like on the 5th or the Friday's class, we'll be discussing some of other type of the bed that do exist. So packed bed is not only the only type of the bed that do exist. And today and tomorrow we'll be discussing some of the positive aspects of the packed bed, some of the problems with the packed bed, and that way it will help you for your design. But the other type of bed that remains there is the moving bed, like the entire bed itself actually moves, and that actually in a packed bed, remember one of the things that which we always say is an issue is the solid cannot leave anywhere. So if the solid cannot leave, nobody can take away the heat, right? With moving bed, the solids flow out of the systems and it can help you. Then also bubbling bed and circulating fluidized bed, their hydrodynamics are different. So those hydrodynamics that Dr. Palla will be discussing today and we'll be modeling that tomorrow. These are all for the packed bed. These moving, bubbling, circulating beds has got a completely different type of hydrodynamics. When you design this, and again, we will be talking about the design equations, and I know we are just discussing with Dr. Palla here that what he is going to cover today and also early tomorrow is that he will be discussing a lot of these design equations. So when you look into the equations he presents there, you need to keep in mind that what it actually caters to. First is mass transfer. So when you actually design a bed, the big issue is that which mechanism is limiting. So quite often you can come up with an adsorbent, might have a very wonderful properties in terms of the isotherm and everything. But when you look at the performance of that adsorbent in a bed, you may only be realizing 10 to 20% of it. So actually it might not even make sense to go for a great equilibrium and all those kind of things, because you may not even realize it. So it's just sitting there, and basically a large portion of the bed may not do anything at all. This is the issue, like as you have done with the plug flow reactor. As you know that we always complain that you have a catalyst which contains costly material like platinum, and you must utilize it, right? Because otherwise you provide platinum, it doesn't do anything. This same issue can happen here. So you have to find out what is the rate limiting mechanism and how do you actually minimize that rate limiting mechanism. The other thing is that these are a lot of these conditions, that what is the inlet concentration and the desired outlet concentration of key species. So I will be discussing some of these from the perspective of your back end, which I discussed also in the first day, that when you design a CO2 capture system, it's not only the upfront, it's not only the capture, but you have to keep in mind what you are doing with the CO2 that you are desorbing. That's very important actually. So we'll be talking about that. The other design criteria that you need to consider is the extent of capture, that how much you want to capture here. Then you need to consider what is your driving force here. The other problem is the heat transfer. So in today's class, we'll be discussing quite a bit in terms of the heat transfer for these beds actually. And that is in the bare bone model that you will have in Aspen AdSim. Lot of these things will not actually, it will not give you access to doing a lot of these things. So question is, how do I embed all of those things? That's a design criteria that we really need to keep in mind. So I know at this part of the workshop, what we are trying to do, we'll be trying to do is that, well, I can build a model in Aspen AdSim. If we can do that at the end of the day, like by the end of Friday, we are in a great shape. But when you go home and start working on the problem, the first thing that you do is that, well, now I can build a model in AdSim, but so what? What do I do with that one, right? Then you really need to think about these design criteria because they give you the performance of the overall system. So we'll be talking more about that. Then the other thing is adsorbent particle size is a very important thing. So what should be the particle size? So when we do it in the lab scale, it's often in form of a powder, right? Now when you take it to a fixed bed and do it in real life, you cannot get it in form of a powder in a pressure swing adsorption or anything. This entire material will be taken off by the gas. It will be taken or carried away with the gas. So you have to have a particle size that will make it stay inside the bed, right? So you have to, then the question is, when you start from the powder to a particle, you might actually land up with a lot of resistances in terms of the mass transfer resistances and heat transfer resistances. So it's not arbitrary. So that is where the people who develop the commercial catalyst, their expertise lies, that how to take the lab scale powder and move it to a real life operations, but without creating the resistances, mass transfer resistances. So that's a design criteria that you have to keep in mind. When you do it in Aspen, sometimes it's misleading. We are looking for a parameter. We are saying, oh, keep the void is like 0.4. But you have to understand that in really, you have to realize that when you put it in the real life, whether you will get a value of 0.3 or you will get a 0.6 or you will get a Knudsen diffusions or you will find out like there is a extreme mass transfer resistances that 90% of the particle is not accessible to the gas, that depends on the structure of the particle, and that is something that we have to keep in mind. The other thing is that if you are using bubbling bed or fluidized bed, you have to think about the fluidizability of the particle, right? When you have this particle, if you say this, my particles, when they heat with each other, they will break apart, then that type of particle is not good to be used in a fluidized bed. Because in a fluidized bed, the particle will collide with each other and they can break only to some extent, but they should not be like breaking into small pieces, because then you cannot have them inside the bed. It will be carried with the gas from the bed. So the particle attrition resistance is an important thing when you try to do this. But now, if you have a particle that is, it's not very good attrition resistance, then you can use them in moving bed. So the moving bed is a good compromise between fixed bed and the fluidized bed, right? Because they have got, these are much packed bed, and it will, the entire bed will move through the system. They do not collide with each other so much like a fluidized bed. So all of those things are important things to consider. Okay, so these are general process design conditions. So anybody has any query for this part?
So actually in real life situations, you see that absorbent particle size, that's really very important. You should be very carefully want to design the particle size. Otherwise what will happen? Normally you see any boiler systems, one ID fan will be there, D fan will be there. Inside you maintain the pressure is very important.
Yes.
Because of the differences,
Yes.
Suppose particles is very minute size in size, it will carry away along with the gases.
Absolutely.
So I think
Yeah.
you have to retain the particles.
Particle
in that
inside
only.
the bed.
But in the meantime, it has to fluidize and interact with the gas.
Yeah.
So that the entire surface of that particle will be have contact with the gas to capture the fluid.
Absolutely.
Something difficult is there. Keep in the real world.
Right, and that is where like a lot of people have come with different type of a structure. Like one of the commercial designers that which we work with, they had the same particle, they put it in a honeycomb type of a structure. So those type of structures give you a very low pressure drop, but it will give you really good exposure to the surface area. And they got this idea from the SCR process, or selective catalytic reduction process, that is used for NOx reduction. If you go to a power plant, you will see SCR everywhere pretty much. So that technology, they got it here and then they do it here. Another one wanted to put it in from a pellets actually. So it's basically almost like look like a blade of a fan. So you put it like this, all these channels, and this will actually flow through that pathways. So you have to be very careful about how you design it. We will not be discussing or be talking about a lot of those things as part of this class, but what I wanted to tell you that our yesterday's lecture was really meant to say that if you know Aspen Custom Modeler, you can do pretty much anything and everything with Aspen AdSim, because it gives you the whole flexibility of writing your own equation, writing your own design criteria and everything, right? Yeah. Okay. So this one is the standard bed, and you have already seen this. The couple of things that you have to remember in here is that for this pack bed, this adsorption capacity is finite, which you think will make sense, right? Because we have a maximum loading, right? So we say, what is the maximum loading that we'll have here? Now, this is also, I keep saying this, that this is an unsteady state operation, right? So what would happen is this, the concentration of the adsorbent will goes up with time. So this will actually load first, then go here, then go here, then go here. And the reason it happened there, and I know that yesterday Dr. Datta was discussed about the breakthrough curve and all of those things there. But the point you have to realize inside your mind here is that the reason that this portion gets loaded first is that they see high partial pressure of CO2. So when the gas leaves from this section, it's very low partial pressure of CO2. So these guys has got really nothing to adsorb. So once these guys get saturated or gets close to the equilibrium, then they cannot capture anymore. Then the gas over here will have higher CO2 concentration, and then they will take their turn, and they will take their turn, and they will take their turn. These guys at the end may never take their turn. It really depends upon their mass transfer resistances and other kinetics there. So a portion of the bed may really do nothing and it has already broken through there, and that's really the thing that you have to think about it. So the question that comes there is, from a design perspective, instead of arranging it this way, could I have arranged it in some other way? Right? This is, and we do not discuss this, but this is known as this typical picture that we are showing. This is axial flow fixed bed. But a counter to this is there is also a radial flow fixed bed. So in the radial flow fixed bed, the same thing is there, but we rotate it sideways, okay? So this portion is sealed. So this could be the gas. Gas in, and this is the gas out. This is gas out. So there is an internal channel, and instead of this passing through this, in a radial flow bed, this is a radial flow bed, it goes here and then moves on the sidewise. So what is the advantage or disadvantage here? Just from the shape of it, can anybody imagine what is the pluses and minuses with this type of bed? What is the key differences between that orientation and this orientation? Sorry? Right, and because of here, it's changing, it keeps changing actually, because R is changing, right? So what happens is that when you come here, you have got a very high cross-sectional area. Here, very low. So this will actually speed up, but here it will actually slow down quite a bit. So if you say, I want a very high residence time over here, this type of bed can actually really help you, because you can design this bed in such a way that it flows through one direction during adsorption, during desorption it flows through the other direction. This type of bed actually leads to very, very low pressure drop compared to that type of bed, and I will show you, if time permits, the differences in the results. So very low delta P, right? So as Dr. Sathuraman was saying, that we have to keep in mind that there is a blower as part of, like, if I'm doing a power plant capture, we have a blower there, and that how much pressure drop is needed for flowing through these ones. So this type of bed are actually very nice for that one. Pressure drop is almost zero actually, negligible because of this compared to the same type of. So this is a criteria that you have to keep in mind. So you can be imaginative in terms of all kind of bed design which many developers are doing. So developing an adsorbent is only one piece of the puzzle, but then there are many others. So that's the point we wanted to mention. Yes, please.
Another advantage would be in the case of large hydroelectric power plant, you need to have very large absorbers.
Right.
Correspondingly with very large height.
Right.
Structurally, it is become unstable. It is just putting line down.
Right. Right.
So structurally, it is more stable.
This is also, as you were also mentioning, that in terms of the height, you can actually take place and you can make it wider instead of making it a very tall tower there. And once you have it very tall, and you will see the pressure drop is also very high. So here it gives you the advantages of doing it this way. But these things do not come without a challenge. One of the challenge that again we know is actually the channeling problem. So so basically when it goes through here, the pressure, even though it's a channel, it is expected to go down. So it might so happen that most of the gas tries to pass through this one, and you may have a non-uniform distribution. So you have to be innovative in terms of your design, that how to ensure that it has a uniform distribution. Yeah, please.
Sir, instead of, we can have a heat transfer, like heat exchanger kind of arrangement, putting backwards and all to increase the residence time.
There are actually, for these ones, people do actually all kind of design to ensure that there is you can reduce the channeling. So it has been commercially done. Even like you could have shroud the half of the bed if you are operating at a lower flow rate and all of these things. So you can make it actually half bed actually. So it will, you can block it like this top corner can be actually put up and down based on your flow rate. That design also exists. And also just like what you said for the heat exchangers, you ensure that it is actually not channeling there. But yes, so all of these gives you a lot of design criteria. So I wanted to say that other side you must consider once you develop the model is the design of this type of beds.
So what about desorption?
Sorry?
Desorption.
Yeah, so for these type of cases, basically the idea there is that, remember what we are trying to do here is they can be co-current or counter-current. So when you do the desorption, so if we are doing adsorption this way, the desorption can come this way, or if I'm doing adsorption this way, the desorption gas can be this way, or both can be at the same direction. So it could be both, it can be co-current or the counter-current. And that's an optimization problem that you have to solve to find out what should be the configuration. That depends upon your gas composition. So if you have a high concentration of CO2 or low concentration of CO2, it all depends on that. If you have a low concentration CO2, you want actually very high residence time for that guy to capture it. So you will push it from this side actually, so that it has got a very high residence time when the partial pressure is high. So this portion of the bed will actually capture more. Here it will speed up, but you also have less amount of material there, so you don't worry about it. So it does not capture much, but I don't have much material here yet because I'm shrinking here. So yes, so it has to be an optimization problem given your bed.
So eventually we can take it out of the parts and again do some kind of mechanical work so that CO2 can be moved. In this case, since it is fixed one, cylindrical type, once CO2 gets absorbed inside the material, so I think it will be some problem to remove that CO2 from this case. That's easy. But how we can remove this captured CO2 from this kind of cylindrical fixed one?
If you really want to move or take out the solid from the bed for regeneration, we should not go for a fixed bed, because then you will have to go for moving bed, bubbling bed, circulating fluidized bed. But because of this packed bed also you cannot take it out, irrespective of axial flow and all of this, because the hydrodynamics will not permit you to do that. If you have to move the solid, you have to go to the different flow regime actually. So that's the issue there. So irrespective of whichever bed we consider, we cannot do that.
No, I could just how to take out the captured CO2 from this two materials.
You'll have to heat it up. So we'll talk about that. It's the regeneration you have to do, and we'll talk about that. That's a cycle setup actually. Yeah, absolutely. That's a cycle setup. But if you have to take it out, I will go for one of this type of bed. You had a question?
Yeah, sir. We have cryogenic air separation units wherein we are separating CO2 and moisture using these dryers.
Right.
So there we have two dryers. One
Yeah.
will be in line, the other will be in regeneration.
Absolutely.
So my doubt is we have packed beds only. So we'll be sending the air. So inside the bed, will that be in a fluidized state then?
No. The cryogenic systems that which you are actually considering, those are all packed bed and fixed packed bed. And the reason why we still work with the fixed pack bed in cryogenic separation, because you are separating CO2 from air. Whereas air CO2 is only in the ppm level. So you can afford to have the bed sitting there for a long time and then you take it out and you do it. But the problem with these type of systems, like if you look into the power plant, as I was saying, this is like an ocean of gas that is pouring through. So it's a 35 or 36 billion ton of CO2 we are talking about. So that is where these thoughts have to come into picture, that is fixed bed sufficient. So I will show you some of the numbers. It can be actually ridiculously high. I will show you some numbers from our studies. Like in some cases, you might need actually 100 fixed bed operating in parallel. So the gas comes and you have to distribute it into 100 beds actually for a single power plant. So that is where this type of bed is very helpful. Yeah, it's because of the quantity of the CO2. Okay, any other? Yeah.
We were talking about radiation resistance. So how moving that takes care of the radiation that we are going to see during the particles?
Yeah, so if you look into the hydrodynamics of the moving bed, so this actually goes like this. So this whole thing actually moves, as opposed to if I'm looking into bubbling fluidized bed, these are much separated. So the gas is there, and because the gas is there, this guy will go and hit with each other. They collide with each other. So gas actually gets that and throws it there. But this is actually more compact bed and flows through the system. So that's how resistance is much less. Okay, unless there is any other questions, we'll move here. Okay, what you have to really need that when the bed must be taken offline, okay, when you have that overall loading goes high. So during that time, you need additional bed, right? So, and we'll be discussing more about that. Like this is a very tricky problem to discuss there. How many additional bed do I need that? So basically what happens is that adsorption, desorption continue with some additional steps in between. And we'll talk about that, what additional steps may or may not be needed for any of these systems. So in general, how it actually looks like, so what you will be finding here is that if you are looking into, this is how it is coming in here, okay? And then this is kind of a saturated zone, this is a little bit saturated, and then it goes there. And then what happens is the concentration actually, notice that if it has already saturated, it is something happening with time. So this is at a given time. So think about a time when this portion has mostly got saturated. Around that time, you notice that the concentration around this section does not really drop. It's a horizontal line because this portion of the bed is not really capturing much. This portion is taking its turn around that time. So if you notice here that this portion, the concentration is going down, and this portion is really doing nothing. So this portion is idling because the concentration is so low that it has really nothing to capture. After some time, this front will keep moving. So this saturated portion will expand here, and this portion will expand here, and this fresh portion will keep shrinking. What we want ideally, if you can, the entire portion of the bed becomes saturated. So this whole thing should be moved here at time. That is where the overall system and the kinetics become so important, because quite often this is almost the best that you can get. By the time it had already broken through and you basically say, sorry, I have to take the bed off. And that is one of the biggest issues while designing this type of bed there. So if you look into it, basically it's the same thing but showing it in a little bit different way. This is showing it with respect to the time. right? So that was with respect to space. Now it is showing it with respect to time. So what it is actually showing you here is that when you look into that outlet gas flow at this time, it is only the top portion of the bed is saturated. Then this portion is actually undergoing adsorption and this portion is clean. As the time progresses, like here, this guy is taking its turn and this portion is now undergoing adsorption. This is clean, and with time this portion is then taking its turn. What you look into at the breakthrough curve is this guy. So what is the problem that we have here is that we do not see what is happening inside the bed. If you're just observing at the outlet, you do not. Oh, okay, sorry. Okay, so if you're looking into the curve here and looking at the outlet concentration, like this guy at the outlet concentration, you see really nothing is happening. So it is T1 here, but inside the bed, the front is actually moving, right? These things is known as the moving front problem. So if you are observing or measuring this at the lab scale and you do a breakthrough curve, this can be pretty confusing because you have no idea what is happening. Suddenly it shows up, but at that point does not give you a very clear indication of what has happened in the bed. That is why we really need to do the simulation, because that will tell you that how much of the bed is actually getting utilized here. So this is basically how it actually looks like. So this is the breakthrough curve here, but just we always define a breakthrough curve for the outlet. But actually the breakthrough happens at every location. So breakthrough means something is breaking through. So this point will have broken through very early, this point has broken through at a later point, and this is the point when it has broken through. Then only I can see it because I'm only measuring the concentration over here. So this thought is actually very important to carry in your mind as you do develop your models and the simulation. And when we'll talk about the performance curve and performance measure tomorrow, you will see that we'll be discussing these things more in details. Okay, any questions here so far? Okay. So there is something called an adsorption zone. This length of the adsorption zone, wherever this adsorption is taking place at any point of time, so up to which it is getting saturated, this is the function of the rate of transfer from absorbed from the gas to the adsorbent, and that is where our mathematical models tell you or let you figure out how it is going. If you have a shallow adsorbent zone, that indicates that it's almost like saying that we have gotten a good utilizations and they will be giving you a step-like breakthrough curve. So if you're looking into this, you really do not want this S-type breakthrough curve. What you really want is a breakthrough curve the ideal breakthrough curve is this. This is, you can say, an ideal breakthrough curve. In reality, what happens is that it will start curving from here, something like that. So this is the reality, or it will be like this. So closer and closer you can bring it to this place, better off you are. Okay. As I said, that only you will see 30 to 40% of the bed is actually utilized, and that is where the problem is there. Of course, the lower mass transfer resistance will lead to longer breakthrough time for the same bed size and vice versa. This is actually one, I will show you results from 2 of our papers. Yeah, go ahead.
Sir, this breakthrough curve is probably assuming we have a Langmuir kind of isotherm and adsorption gets saturated. But it is like, if it is like PET isotherm or any other isotherm which has multiple peaks and all, will that be so simple?
It will not be. This breakthrough curve has got 2 assumptions here. One is in terms of the mass transfer resistance, how you are modeling that, and what type of an isotherm. It's a result of both of them. But depending on the type of an isotherm, there could be multiple breakthroughs. So there could be even cases there could be even cases like these and like these, and yes, all kind of breakthroughs are possible.
Yes, because second layer starts accumulating.
Absolutely, yeah, that's a good comment. Yeah, it all depends upon isotherm model, kinetics, and what is the dominating impact that you have. So this is something I thought I will bring from one of our papers there, and which kind of shows you that how the breakthrough takes place. So look into here, like this is one of the papers we did. It's a fixed bed reactor, but it's a micro-encapsulated solvent. Again, you can think about this as a sorbent, but this is basically like if I take you a balloon and put water into it, but instead of water, you put a solvent inside it. Okay, small particle like 50 micron balloon, and then within that 50 micron balloon, I put a liquid in it, and that is this guy actually. This micro-encapsulated solvent. This is not our technology because we are modeling people. This was done by Dr. Josh Stolaroff from Lawrence Livermore National Lab. So it's and Catherine Hornbostel. Those are the technology developers for these ones. But nevertheless, this shows you that how the breakthrough looks like. So look into that. There are 2 things we are showing here. So first thing is that you see that this is showing it with respect to time. Now, if you are looking into the breakthrough here, right? So you notice that towards the entrance, so one is the entrance, you get the breakthrough at any given time right away. Then another time you are seeing this, and this is a front that is actually progressing. And then what you see, the loading of it, the loading actually does the same way. So the front portion does not load at all. The later portion start loading here, and that other portion actually start loading afterwards. Okay. So this is one interesting thing that what you actually can find out, that with respect to the bed. The one thing not to confuse this, that this time is actually residence time. So think of this as about the length of the system. Okay, so not to be confused with the breakthrough time or actual time. This is the residence time. So this is actually the length of the system. So up to this is like the length, the entire length of the bed actually. So, but this gives you a very good idea how this font actually keeps propagating. So keep in mind here that if I'm at 75 seconds, for example, it already broke through from the beginning of it. Kind of, right? And at 100, you see there is really not much of a difference, because actually this guy is not doing anything at this point. Now, when you go to the middle of it, you will see already it started showing up over here. At that time, there is really nothing happening over here at 75 seconds. and then at the 100th second time, you will see that actually it started showing up. But all of them are going to the same value. But if I would consider the breakthrough here, it has already breakthrough just in the beginning. This tells you that how the bed should be sized, because if my bed size would have been for the residence time here and my breakthrough was somewhere here, I have almost instantaneously broken through, right? So this gives you that what should be the bed length. So this is how you actually can simulate a very long bed, and then looking into it, then you can actually chop it and say, okay, this is where my bed size should be. So you can do always a longer bed, and then after you simulate these breakthrough curves, that will actually help you to design the bed there. So that part. And the corresponding thing here is actually the loading, and you see that front portion, it actually the loading does not change very much after some time, but in the second and the third portion actually then take their turn and their loading actually keeps going. But the interesting thing to note that is the front portion actually goes to the maximum loading here, but these portions only after such a residence time will give you that same amount of loading. So if I would have my bed length like this, like if the bed length was equivalent to this portion has so much of the loading, this portion will have like a half of the loading, and this portion really doesn't capture anything. And this is the issue that which I was talking about, that you have to really think about that part. Another result I'll show you is that this has got a temperature. That's what I wanted to show you here. This is so the one that we had over here, this is a solvent. And you might argue, why you are using a solvent here, putting it within a balloon, rather than using a distillation tower, right? That's a natural question. This is actually a solvent that we are using. These are actually highly viscous solvent. So it is so viscous that it will actually doesn't want to flow through the distillation tower, or you have to basically heat up quite a bit and all of those. But this has got a very high capacity there. And if any of you are aware of it, like if any of you are from natural gas sweetening processes, or you know those processes, there is this hot caustic wash processes people have used for sulfur removal, right? Potassium hydroxide and sodium hydroxide people have used there in natural gas sweetening processes. You have to heat it up to quite a bit temperature to actually make those guys flow, those solvents to flow. Otherwise, it is very viscous. So if you have a viscous solvent, this is the way to utilize this. Like I'm not a technology developer, so I do not know this. This is specialized equipment that these guys actually develop, that in a 50 micron, this guy comes and put the thing and put it in the balloon, put it like a drop of solvent and put it inside the balloon. So it's a complicated manufacturing technology, but that is why we did that actually. It's a solvent. This guy is a metal organic framework. This is my student Ryan Hughes actually worked on that one, and this is a diamine appended metal organic framework here, and Professor Jeff Long from University of California, Berkeley actually is one of the lead developer as part of this work. Actually, Rebecca and other guys from their group also was actively working with us on this one. So this is even more interesting. This has got a very high heat of adsorption. So see what happens when you have a high heat of adsorption. So this has got about 65 kilojoule per mole heat of adsorption. So if you look into the loading, even with respect to time, you see at the entrance, it goes up and then first it goes up very quickly, and then it slowly goes up. The second portion, the middle of it, now takes its turn, and then at the end the exit takes its turn. But this is the maximum loading that you could have gotten for this metal organic framework. But in reality, you are getting the more than 50% of the bed is only getting 2.5 over 5, like only 20% loading than what you could get from equilibrium. And the reason is because the temperature is going up. So the moment it captures, this is the issue with the fixed bed, because when capturing it, the heat is released and it will immediately shoot up. Immediately when it shoots up, it will affect your isotherm. So again, when Dr. Pala actually discusses all of those today, and I know yesterday you had some discussion about the isotherm, you will see that it does not favor your equilibrium. So higher temperature hurts you in terms of loading. So temperature goes up. That's why you never can capture this. So you notice that they go to the same loading because they go to the same temperature. Now, looking at this curve, can any of you guess why this shoots up and then slowly starts increasing? So it's almost like a step-like thing, and then it slowly goes up. Exactly. The temperature, you see the temperature drops, and then temperature increases first, and then the temperature drops. So this temperature drop corresponds to this increase. So why does this temperature drop? Right. So your heat, exactly, the heat that is taken away from the convection is more than the heat generated due to the adsorption. So you see that this how each other, right? So at this point, the heat generated through adsorption is much more than the convection. So the temperature shoots up. But later on, it's the convection which is dominant, and that's why the temperature drops. As the temperature drops, this favors these ones. This is also done using AdSim. However, this isotherm.
Same thing is applicable to middle also, middle and edges also. But here temperature drop is not there. In the first case only the temperature drop is there.
Correct.
Does it mean that in the middle there is no convection?
No, there is convection. So this is a great question. And anybody wants to take a shot at it? And I was trying to get into that one, but yes.
It is losing, and the middle part is losing the heat due to convection. The heat from downspace is coming there.
Exactly. That is what is happening. So this temperature that from the front portion, that is cooling, but because it is cooling, the later portion is already getting the flue gas which is already hot, so they cannot cool down. So when this is coming, the gas is coming at 25 degrees or so, okay? That's why this front portion cools, but because the front portion cools, the gas already gets heated up. So when it reaches the middle portion, it is already hot, so it cannot cool it down. It's very interesting if you really think about how this happens, but the mathematical model will actually show you all these complicated interactions that is taking place. Okay? Okay, so I will be switching the gear a little bit here. So now we'll be talking about the regeneration of the bed. I avoided the math here because yesterday we discussed about how to solve the equations. I know Dr. Pala is going to discuss good bit on the adsorption models and the equations there. But I just wanted to tell you that these dynamics, AdSim will capture it, all of these dynamics, and very nicely. So when you analyze these ones, it will show you. It's very insightful. Sometimes looking at the equations does not tell you really what is happening. And then you start realizing why it fails to converge, what happens, what is happening. This is very interesting, actually, from that perspective. So this is the traditional approach, pressure swing adsorption, like the one that you were talking about, the cryogenic separation, right? That's very traditionally used pressure swing adsorption. Another pressure swing adsorption process, can anybody give me an example? Extremely widely used pressure swing adsorption process. correct, nitrogen, hydrogen, correct, like all the PSA hydrogen processes are all using the pressure swing, and it's very interesting if you walk into one of these plants how they operate. So let's look into how mathematically to consider all of those things. So basically what happens is this is the feed gas, right? And this is how it goes through these beds. So if you're not very familiar with any of these, let me try to draw these a little bit and so that you kind of know how these pressure swing adsorption systems are actually set up in reality. So if you have and so in general, when you are looking into the adsorption process, like this is the feed gas that is coming into this system, there what is really happening is that if this guy is in line, this is closed. So this guy is undergoing adsorption. So this is only thing it does at that point of time, that this is undergoing adsorption at that particular time. And then what you really do that after some time, when this has already taken its turn, then you have to put this guy in line, right? For doing that, there is first thing that we call it a pressure equalization. So this bed would have regenerated by this time, and this one is actually doing the pressure equalization. So that is why this valve is there. So when this is undergoing adsorption, this valve remains closed. When I want to take it first, I have to first open up this valve. So first step, adsorption for bed A. So this is A and B. Before I take bed B in line, I have to equalize the pressure. What I do need to equalize the pressure? I will just open up this valve and the pressure will be equal, right? Yes.
Sir, you say compressor energy that is going to feed in the next feed distribution, and also because you have some amount of product gas that is available at the top side of the column that you recover in the other column, so that enhances your recovery also. So these two basically take care by the pressure equalization.
There is also one more practical thing. Any other point? Those are very good points. Exactly, you said that. But there is also one very, very practical points. Let's say I do not worry about getting the materials here. And what I basically say is, I want to do this guy take in line, just close this valve, open these valves. Instead of equalizing the pressure, what will happen?
That will be utilized at the bottom side in the impurities that you will capture in that top side.
It's actually a little bit real life. If
See, the flow rate is too high, sir.
exactly because of
It will be restricting because the outlet will not be open at that time. The dryer B's outlet will not be open.
right. The point here is, if it is not equalized, assume that this is 6 bar. This is 1 bar. So very high driving force. The flow rate will be so high that this will raise the bed actually. So whole bed will be lifted, and this guy can actually be carried from the top. actually at the top of fixed bed there is always a restrainer. So people use all kind of things. I have seen like starting from that all the coconut shell type of things at the top to lot of sophisticated screens and other things. People use it to restrain the thing on the bed. But when you have this, because you have a very high driving force, it can actually break those things and take it away. So you do not want that. That's why you slowly bleed. This is a very small valve. So if it is like 2-inch line, this could be like 1/4 of an inch or something. So you slowly bleed this so that you bring the pressure into equalization. So then you basically say, then your second step is bed adsorption, I will say pressure equalization. Then I will say the third step for this one would be, so second step is basically you open up the valve here. So you open up the valve over here. So in the third step, what you really do here is that this wants to go to regeneration, but you will have to first, so what should I do this? Should I open this first or should I close this first and then open it? Because right, because otherwise I'm interrupting the flow rate. If I close it and do not open it, your gas flow will go down immediately. So if you're operating an air plant, your flow rate will immediately drop because I have not opened it here yet. So before you close something, you must open the other side, right? So third step is that take bed B in line, right? So basically what does it mean is that you open up this valve and then you close this one, you open up that one, and you close these guys. So now this will be in line. Then the fourth step, you actually, generally you do a blow down, which I actually mentioned over here that it can be combined. It really depends upon what you are talking about. Whether you require first a blow down and then you need a deeper depressurization, it depends upon your application. So that's why I put it this slash. It really depends upon what you are really doing. So blow down, depressurization, and all of that. And then this fifth step is optional for many systems. Like you may need to purge. It depends upon what material you have and all of those things. So purging is really, it depends. Like purging, I will say if needed. If we need purging, then only we use it, otherwise we don't use it. And then this cycle actually keeps going on there. So this is the standard pressure swing adsorption cycle. That's how it does. It looks simple, but when you start putting it mathematically, this is one of the complicated problems. And why that is the case. From our discussion yesterday and today, we will not be doing the cycle setup, to be honest with you. I was talking to Dr. Palla that I will probably give you some example problems and you can try it at home. This is very complicated, doing the entire cycle. So we'll see how our overall tutorial goes tomorrow, and then you will be doing those things. Probably will take some time to do it. But what is the challenge of setting up this cycle? So first thing what you have to realize here is that even if I am doing this adsorption cycle, when you close these, this flow rate is 0. So if I'm going to a desorption cycle, and for the desorption, if I'm simply doing a valve, right, here, I did not show that portion over here, and this is for the desorption, right? So that time this will be open, this will be closed when this time comes. So when I do the desorption, like this step here, I close this valve, this flow rate going here will become 0 immediately. This flow rate through here will be immediately going through the valve will be 0. And I did not get a chance to discuss that as part of the ACM model. One problem with the 0 flow rate is that Aspen cannot establish what is the composition of it, because nothing is flowing through the system, right? So because it cannot establish what is the composition flowing through the system, because there is no flow there. The problem is it cannot do any of the properties calculation. So moment you try to do it, you will see in the message box, thousands of messages will show up, all coming from the properties call. Because this properties call, the arguments are all empty, because it doesn't know the what compositions at which you are trying to do it, right? So that's challenging. So many times you have to keep a little bit open actually, so that some flow goes through and it can establish that. So 0 flow is a problem for any of these cells. So there are specialized way to set it up, kind of almost like forcing some of the equation not to solve, and say, do not worry about these ones because I'm not considering this. That's all about the cycle setup. But it's actually a little bit difficult mathematically. In real life it happens, but mathematically this is a challenging problem that you will actually see that occurs here. Okay.
If you maintain the minimum flow, instead of 0 flow, then it cannot be 100%
Yeah.
disaster.
But it can be very low. Like for example, if you are sending product through a system, say 100 mole per second, you can put it like 1e minus 5 mole per second, something there. So that can help, but Aspen has done really good job, and that is why that inbuilt model actually helps. They have made a lot of those things internally, but if you code it yourself, you will run into trouble, because we have coded all of those, whatever is an Aspen AdSim, we have coded everything ourselves, and I know what the trouble it actually goes through in setting it up, and we had to do all of those things to put it.
This is the things I am thinking, sir. Whenever we are using the simulation kind of software, other things like Aspen, because it isn't developed by some other firm, I don't know how it's developed is it. But when we are applying that software, simulation software here in India, seeing the particle conditions, seeing your own experience, and we are also including our the input everything. Have we modifying that Aspen software, or still we are simply following their own? Because when you are implementing in the field, naturally based on your experience, you'll be doing some changes.
Right.
That whether getting implemented or still it's.
Right, yeah. Meaning we have recreated Aspen AdSim because there are certain things we wanted to do, AdSim could not do it. So we had to write the whole thing. And then when we write the whole thing, we realize that what issues that it actually come in. Like for example, we wanted to do the radial flow bed. AdSim will not let you do the radial flow bed. It will only do axial flow bed. So for the radial flow bed, we had to write everything ourselves. And then when we try to set up the cycle, we know these issues will keep coming. Actually, these issues will keep coming. So that is one of the problems that which we have. So we have to keep in mind this overall thing that we have over here. Okay, yeah, we are good. Okay, so these beds will operate under cyclic conditions. So remember that one. And then how many beds we need? This is a very tricky problem. How many total beds we need? This all depends on why did the light goes off? Okay, so the total number of beds will depend on the duration of each of the stages and the number of the stages that which we are considering. So, as I said that in real life, if you are processing a large amount of flow rate, you might need say 50 bed in parallel in adsorption. If I need, for the sake of our argument, say 50 bed operating in parallel, how many total bed do I need? For simplicity assume that 3 beds in parallel, assume that in parallel undergoing adsorption. How many total number of beds are needed? I need 3 in parallel undergoing adsorption. Do you understand that some of these beds are undergoing desorption as well? How many beds do we need? Sorry? 6 was one answer. Greater than equal to 6, one answer. Okay, very good. So take a shot at it. So how do I know how many beds I need? So I showed you like one bed A has got bed B, right? So I just showed 2 beds. Like I needed 1 bed in line, so I needed 2 beds. So
suppose the number of the bed sheets and the size is more or big in size than the adsorption, then it can be one also. So again, it depends on the size of that Gantt. Minimum, yeah, 1 to anything, 1 to 3 you can have. Suppose you have very big in size compared to 3 adsorption small size one. Single big size can be enough, I think, or 2 or 3.
right. So there has to be some thought there, right? How do I calculate it?
It also depend on how many number of steps are there and what is their length in time.
Right. So of course the duration of each of the stage. Can you see how somehow this pointer is not working? It's because that hold on. It works here, but somehow. No, I think there's some connectivity thing here, right? Okay, we'll discuss this in the meantime. So duration of each of the stages and the number of stages, right? So maybe it all depends upon the duration of each of the stages, right? So I may need 3 bed, I may need 6 bed, I may need 4 bed, I may need 5 beds and all of that, right? So I'll show you this calculation. So how this is done? This is done, I think this is maybe some connectivity thing. If you just quickly have a look into the thing, I can see it here, but it was showing it on the board, right? Is it some switch thing here or something got turned off? So it actually, you need to solve a scheduling optimization problem. And that is not something which we are going to do it, but I will show you mathematically what it does. It's a mixed integer linear programming problem that is done. So typically this is a optimal scheduling problem. It's actually a mixed integer nonlinear linear programming problem. But one heuristic that you can apply if you do not want to solve this one, there are a lot of work here in this. Heuristics adsorption time divided by the number of adsorbent beds in parallel at any point of time. Must be greater than equal to the total non-adsorption time divided by the number of beds undergoing non-adsorption steps. And is it working now? Thank you so much. And then the total number of beds is equal to number of beds undergoing adsorption as number of beds undergoing non-adsorption steps. Remember, I did not say desorption, I just said non-adsorption. This will include everything like purging, blowdown, anything. That is that it is not doing adsorption. That's all it means actually. So, this is the heuristics. In reality, you have to do some other aspect also. I don't have really much time to discuss that, but let's see, I can, if time permits, I will show you a quick Gantt chart of how these systems actually look like. Let's see if I can finish this portion before 12. I will show you actually how this schedule actually looks like. I'll try to draw it here and show you how actually this schedule looks like. And I'm sure you guys have done the Gantt chart before. This is a standard approach of a batch processing. If you have taken a batch processing class, like all the pharmaceutical scheduling and all of those that is actually routinely done. So I will try to show you one if I have time permits. But this is one of the way that you find out the number of total number of beds there. Okay. The other thing is the regeneration of the bed is doing by the temperature swing adsorption. This is probably the most important technology for CO2 capture. And I will tell you later on why this is really the approach for many systems that people follow it. That point is later, but let's first understand the technology here. So what you really do is that when you are done during the adsorption, you use something like a cooling water. This cooling water flow in an embedded heat exchanger. So it's an integrated heat exchanger that sits within the bed. Many of you have seen, like for example, some of these DeNOx technologies, people use it for cryogenic separation processes. you have seen, like especially for the moisture removal and other places where there is very high humidity and those type of things, and also for some of the separations of other contaminants, there is there an electric heater. People have used it. That is for heating purposes, right? So that is the same thought here, but it's actually cooling is doing by the cooling water. When you try to regenerate it, you actually put it a hot water through the system, right? And then you do the sweeping here, and then after that you actually cool it back again, and then it goes to the adsorption. So you might need an intermediate cooling step or before it goes to adsorption. It really depends. Some of the sorbents, if you do not cool it, it will break through immediately. For some of them, actually, you can skip the cooling step completely. But generally, if you are doing a temperature swing adsorption, the idea is that instead of pressure, you raise the temperature during desorption and then cool it back again before the adsorption. So that's the overall process. Now the question is, how do you heat it up? So remember here I just said hot water. You can use steam, for example, for heating up the bed. But remember, if you are using the steam for heating up the bed, steam by itself does not give you much energy if you do not condense it. The main energy content in the steam is in the latent heat of the condensation. But if you are not condensing it and you are just saying, oh, I want to use the sensible heat, you need massive amount of steam that goes through the system. So it's usually not worth it. So putting it within a hot water and actually can really help you from that perspective. But this is all about that what you need to do for temperature swing. Yes.
Won't steam condensation inside the bed leave like bed completely moist?
It's not desired actually. So you cannot condense it within the bed. That's the problem. So if you do not condense the steam within the bed, that means the amount of heat that you can get from steam is only the sensible heat, which is very low. That is why it's not a good idea to use steam for heating. If you use steam, it's only for reducing the partial pressure. So you can use some direct steam injection during temperature swing. So I will be so you are right. If you actually the steam condenses, it will be actually lump. And interestingly, I know one technology developer who was actually trying to do something like that for a moving bed. Actually, it's the solid cease to flow because it formed lumped and the bed will not flow through the system. And the problem is that from the boundary condition, it was not showing that the water will condense. It's because of some capillary effect somewhere inside it was actually condensing, which we simulated and we found out somewhere in the middle it is actually going to the condensation conditions there. But what I would like to mention here is that steam should not condense in the bed. If direct steam injection is considered for heating, only sensible heat content in steam should be used. So it may require very large quantity of steam. direct steam injection, it does not mean that you should not use it. Direct steam injection can help to lower the partial pressure of CO2, so help in regeneration. Right?
Another question is now, if suppose you are using hot CO2 for desorption,
Uh-huh.
now won't something like what happens in case of evaporation, air becomes saturated with moisture, like that it happens because the partial pressure of CO2, already 100% CO2 you are passing and you want to dissolve CO2, so
Right.
you are at the end of the isotherm.
Yes, so you might require a higher temperature if you are using CO2 there. The other thing you have to also remember, if you are using a gas like CO2, gas CP is very low, as we all know, right? Specific heat of gases is very, very low. So if you want to provide this 65 kilojoule per mole or 100 kilojoule per mole, you have to send actually massive amount of gas through the system. It does not matter whether you use CO2 or nitrogen or anything. This is because of the scale that at which we want to go to, because of the amount of heat needed is very high, and generally gas, providing it with a gas sensible heat is not a good option unless there is a very hot gas, like you say, I have a 500 degree centigrade temperature gas that I can pass through, but that may not be acceptable for the adsorbent. That high temperature may not be acceptable. So we have to keep those things in mind. Anything else here? Okay. The other thing is that this is also from Ryan's paper, because we really wanted to look into this. So we consider two processes. One is like we call a basic TSA process. Basically, idea is that there is no cooling needed during adsorption, and during desorption, we have a heat exchanger here, and we put the steam inside the heat exchanger. So it does condense. So instead of hot water, I can put steam inside this one, and it will condense and come out. So this is one approach. But you see that there is also a steam being injected over here. So this is the direct steam that I was talking about, that helps you to reduce the partial pressure of CO2. This steam is not for heating. This is the steam used for heating. So the problem here is that you are not able to cool it here. So now if you actually use it for cooling purposes, so you can use a cooling water. If you put a cooling water here, for the desorption step, you cannot put a steam in the same coil, because, just to ensure we understand the question. Say I put a cooling water, so I have a coil here. Instead of keeping it empty, I can put a cooling water through here for adsorption. And then what I do is for the desorption, you see that we are suggesting you put a hot water. Instead of hot water, once the adsorption step is done, I can inject the steam inside here instead of hot water. What would be the issue? Right, and so what would be the problem there? Because if steam condenses, I'm getting the heat anyway, so I'm happy with it. It's an industrial problem, it's practical. Sorry? Let's say we keep the similar temperature that I wanted. There is something called a hammering, water hammering. So it will lead to water hammering because the steam will try to push the water and it cannot actually, because steam travels at a much higher velocity. So that is why we always have the condensate removal and all of those. So it's a practicality problem. In real life you cannot use it. Mathematically you can, but it will cause the water hammering if you introduce steam directly into it. So that's why we proposed when you use cooling water, use hot water. So and then the hot water is heated elsewhere by using steam in a heater, and then it just keeps circulating. So that's how it is. Now this gives you some of these things here. We consider bed length like 10 meter, bed diameter 10 meter, blah blah, and all of that. The reason I wanted to show you here is there are some interesting results I wanted to show. I think actually maybe I will okay, maybe I'll discuss that actually after this slide, but this one connects to some other slide later on, but this is overall thing. I'll come back here later on. Okay. The other approach is to doing the vacuum swing. This vacuum is actually pulled for regeneration. So basically you pressurize it, adsorb it, depressurize it, evacuate it, and that time it basically, if you have strongly adsorbed CO2, like more because of the chemical reaction, then you might require vacuum here. So that is where you do the vacuum, and you can also do an inert purge like nitrogen and steam, etc. And you can actually use those things for purging the overall system. So that is basically the whole idea of the vacuum swing adsorption. All of these actually can be used in combination with each other. So I can do simultaneously pressure and temperature swing. I can do, and we'll be talking about that, some of these other approaches where you pressurize it and then you actually pulling it out, you do the vacuum swing. So all of those approaches, these can be combined. These are not exclusive. You can do a combination of all of those, and that is where your design space become larger and larger and larger, right? Any question here? Okay. If not, I will now go into how this will actually look into. So think about like a power plant. So how it will operate here is, again, this is from Ryan's paper. So this is the gas, this is coming to a compressor or a blower, and you see how these are actually put into the system. So if you have a parallel bed, these beds will be in series and in line. So these are empty valves, and these are undergoing regeneration. And then you will see that when you actually get the gases out over here, this is the steam plus CO2 that is going out. If you have the water that is, or condensate, or the steam that is going out, this is how will the condensate go out. So this gives you a showing an idea in reality, if you conceptualize it, how such bed will be operating, how many beds you will be needing, and those scheduling problem you solve separately, and then you design, find out the n number of beds and come up with a cycle design here. But this is the overall configuration that you consider. Now, when you have a vacuum here, so then you pull the vacuum here. So this goes to the vacuum, and then it goes to the CO2 compression train. And that is what the problem is. So that is something you cannot forget about that part. And I will say you why that thing actually keeps coming. Okay, any question here, anybody? Okay. Now, one thing which you have to remember is something called a cycle design. Maybe I was planning to do it sometimes also tomorrow as part of the tutorials, if I have time permits, that how to set up cycle in AdSim and discuss more about that, and some mathematical nuances. But the conceptualization, I wanted to do it today. The first thing is that, as I said, you really should be solving a scheduling problem. The heuristics that I gave you, that one thing which you have to remember here is that if the CO2 that you are regenerating Only thing I said that when you do adsorption, it must be continuous, like all the beds should be in parallel. But what happens to the desorption? The gas that is coming out from the desorption, that is being compressed by the CO2 compressor. What happens that there is a gap between the desorption. So bed 1 dissolved now, and then there is a 5-minute gap. After that, bed B comes for desorption, and then there is a 5-minute gap, then comes to the bed C. If there is a gap between the bed desorption time, the CO2 compression or CO2 compressor will not like it, because it's going to zero flow, right? Or one bed is desorbing, so in the beginning of desorption, you dissolve lot of CO2, so flow rate is very high, and then towards the end of the desorption, the flow rate will go down. So you are talking about a fluctuating flow rate to the CO2 compressor. So you have to be, that is why the scheduling problem is so important to solve here. This part is, my observation is that this part has been normally been very neglected in the literature, but I will point you to some of the papers in this area, including one of our papers that where we actually tried to define it and do it like that. But the idea here is CO2 flow rate to CO2 compression with time. If it is like this is not acceptable. This is not acceptable at all. So this is one extreme. Other extreme is like this. This is also not practical because of this cycling process. So you will have to see something like this. So you basically say this is the acceptable variation. So this is the acceptable variability. Plus use a large surge vessel or storage vessel to smoothen it. So at the up front of it, you put a vessel which will actually take this, and then it will smoothen this pressure, the overall systems in here. But this is something you have to keep in mind, that going to zero is not acceptable. So that is where the challenge of the scheduling, that is why you need to solve an optimization problem to satisfy that constraint in there. Okay. Now, this bed design which we did for 90% capture from a subcritical pulverized coal plant for 644 megawatt. Notice that number of bed undergoing adsorption is 12. See the total number of beds, 43. So the other beds which undergoing other steps, in this case there were actually 31 beds undergoing that. That is for that basic TSA process that I discussed here. Like if you are doing this cycle. If you are doing this cycle, then there will be 3264. It just becomes exactly matched with the time. So you see the total number of beds is actually undergoing adsorption and desorption. This becomes actually very different. You see the cycle time also, how it becomes different. So as you are doing the bed design, all of these things are going to change, like optimal residence time, the adsorption cycle time, desorption cycle time. All of these are design criteria that you are keeping in mind for any of the system design. Okay. So when you try to regenerate, develop the model, one questions come here is that are there differences? No, you use the same adsorber model for doing the regeneration. So mathematically, everything will work out the same way, but adsorption is taking place in presence of, say, CO2, nitrogen, moisture, and whatever. But desorption is taking place only in presence of maybe CO2 or steam. So you do not have nitrogen. So you are changing the composition of the gases completely, and that is where this becomes a tricky problem, that you have to change the boundary accordingly. Then you may need additional model because of the embedded heat exchanger. This is not something directly AdSim model will give you that, but I'll show you. Let's see how the tutorial goes tomorrow. We'll show you some of these advanced option, that how to include this heat exchanger and where to write the equations for any of those. As I said, that there could be change in the boundary condition. So as you notice here, so when the adsorption is taking place, the gas is coming in, but when you move to the desorption, instead of gas, it is a steam that is coming in. When it is going out, this is the flue gas going out, this is the steam plus CO2 going out. Then the idea is that when you have an adsorption, this is cooling water coming in, this is hot water coming in. So all of these actually leads to stiffness in the solver. And so that is why understanding Aspen custom modeler is so important, because many of these things, the bare bone Aspen AdSim model does not give you the directly in their library. You can build all of those, right? That is what all our papers are all in that area, because we tried to build all of those things. You can do it, but you have to be careful, because every time you are actually doing it, this is leading to a change in the boundary conditions. So that's the part you have to understand here. The other thing you have to keep in mind also is that the operating condition will change significantly. Like the environment which has got only nitrogen and CO2, it will suddenly see only steam and CO2. So the compositions will steeply change inside the adsorbent, and that's a problem because of, as we discussed for any Newton type of a solver, how to do that transition there. So there are tricks that you can do for doing that. Now, one question comes is what type of cycle is optimal? The answer really depends on the feed composition and the available pressure at the boundary. If the feed contains large amount of contaminants like nitrogen in post-combustion flue gas, so this is different if you are considering a blast furnace gas versus you are considering a steel plant versus you are considering a pulverized coal plant or NGCC. What is actually in the boundary? Then first thing is that only let's say if you have large amount of nitrogen, just as you will expect in a power plant, only a moderate increase in the flue gas pressure is optimal. All our economic calculation shows if you go out from the blower regime to compressor regime, your economy it goes down, because you are compressing nitrogen, right? That is what the problem is. So that is why the pressure swing problem, only pressure swing has limitation for post-combustion capture. It's not expected to be optimal, because you cannot, if you look into the economics of it, compressing the large amount of gas consumes so much power. If you're trying to compress it, that actually causes economically unfavorable situation. So what you really want to do is that it is okay to compress some using a blower, but some temperature swing is expected to be needed. So it's basically a pressure temperature swing approach, where you can lower the pressure during desorption and temperature needs to be increased for desorption. So you can do a combination of both of them. I wanted to ask all of you a quick question. So when we do the pressure swing, so in the temperature swing, we do the desorption, right? So the thermal energy provide the energy for desorption. But in a pressure swing, I pressurize it and drop the pressure, I get depressurize it. Who provides the energy for desorption? Nothing is free, right? I talked about the no free lunch theorem, right? Nothing is free. So in temperature swing is obvious. I provide the energy and desorbs it. But in a pressure swing, I do not provide anything. I just basically drop the pressure and the gas is coming out. So where from the energy is coming from?
You already provided in compression steps.
In the compression state. So the power requirement for the compressor is the main parallel to temperature swing. So the thermal heat I provide versus the compressor power that I require, that is the thing that you need to compare to see where it is actually coming from, right? The other thing is that only moderate vacuum, if at all needed, is expected to be optimal, since CO2 need to be compressed to 150 bar. This is something you just need to look into the number to realize what I mean here. Assume CO2 is dissolved at, I put it like 150 bar, take that one itself, at 1 bar. Then compression ratio is 150 over 1 is equal to 150. If CO2 is dissolved under vacuum at say 0.5 bar absolute, then compression ratio is 300. And if I do it (0.25 bar), compression ratio becomes 150 by 0.25, 600. For many processes, this CO2 compressor actually consumes almost like 50% energy as the capture system itself, almost, when the CO2 is available at 1 bar. That is why only a very moderate vacuum is acceptable. And so even though all of those are mathematically possible, all of those works for other type of system, but for here, because we want to ultimately compress the product to such a high pressure, the vacuum is not expected to be economically optimal. For temperature swing, I would also like to mention that you desire the adsorption time is relatively high and the time for heating the bed for desorption is not very high. Because if you say I go from adsorption to desorption and if it takes me so long to heat up the bed, then the temperature swing will not work. That is why that embedded heat exchanger and the design of that embedded heating process is so critical from that perspective there. So that is why, as I said, embedded heat exchangers are very critical overall. So in the conclusions, I would like to mention that economics is not only the adsorption. Adsorption is only the part of the game. You must look into the desorption, and most cases it's actually the desorption that affects the overall economics. That has got the maximum impacts on the overall thing. So just looking at the adsorption can be very misleading. So total systems you really need to look into it. And from that perspective, you need to come up with an appropriate design for this overall process. The cycle design is one thing which I'm missing here, and I have got a couple of minutes here, so I'll just show you quickly how it looks like, or it will look like here. but you must solve an optimization problem. This is a mixed integer linear programming problem, which we would not have time to cover as part of this class, but that's how those things are done. And I will basically first see if anybody has any questions. Otherwise, I'll show you how a cycle actually design looks like. Any questions? Okay, so I'll just show you graphically, but you show when you think about it mathematically, you have to pose this as an optimization problem. So I'll say the cycle design. I'll show you by a Gantt chart how it actually looks like. Assume 3 beds in parallel, say 30 minutes of adsorption time and say 5 minutes of non-adsorption time. So based on my calculation there, what was the thing, how it should be? I said 30, remember that equation that I wrote for a heuristics. You can apply for simple calculation. 30 divided by 3, so 10, right, should be greater than equal to, I said 5. So if I'm just using one bed, that should be sufficient. You see, if you have that equation written up, you can actually correspond to that one. So this is basically the non-desorption time, and this is my unknown. So I'll put a asterisk mark. And as a guess, I will just put just one bed. If I do this, this is satisfied. So I basically saying total number of bed is total number will be 3 plus 1. So I need 4 bed for these systems, right? So let's see how it actually cycle that will look like. So if I'm actually doing it over here, so I will have so this basically means adsorption. This is my bed A, and this is, I'll put the scale below, and then assume that I'm starting it another one 10 minutes later. So this is 10, this is bed B. So this bed after this will go for desorption, and this bed will sustain for another 30 minutes, and then assume that I started another bed. This is 20, this is bed C, and then what you really find there is that at that point of time, that 30 minutes later, I need a bed to start here. So this bed is after that. So adsorption, this thing, this is actually non-adsorption, and this is idling. then this bed will go for 30 minutes. And here what happens is that this bed comes out, then it will go for the non-adsorption, then it will go for idling, and then it will start here. The same way it will happen with this bed, non-adsorption, and then idling, and then it will go for adsorption. And this bed will do the same thing, idling, and then it will go there. So what you will actually notice, so that is the point you need to follow along with me. Look into here, right, after this, and then after that it will go for regeneration and do the idling, and it keeps continuing with the adsorption here. So if you notice from here till here, this is your cycle time equal to this 30 plus 10, actually 40 minutes. After that, if you actually draw it in front of you, you will see that it will actually keep repeating. So I will have exactly the same thing. So if you look into this particular bed, here I started with here the regeneration. You see I am again starting with the regeneration here. Here I spent already 20 minutes over here. I'll be starting about 20 minutes over here, and I'm starting here. Then for this bed, I have already started 10 minutes. I have got 20 minutes remaining. So these beds will keep going here like that, just like what we had over for these ones. So this is a repeating cycle that actually keeps going. And so the trick for this one is that you actually, when you start drawing it, you actually offset the time in the beginning, and then at one point of time it will actually catch up there. So that is how you do the Gantt chart. And if you have done a batch processing class, this is something which you routinely do. If you plot it in Excel actually with these blocks, you should be able to find out that these overall systems become really repeating for these systems. So now the thing that is happening is that adsorption, non-adsorption, and you see there is a 5 minute of idling. You see there is a gap everywhere. So the CO2 compressor during this time is not getting anything. Then it is not getting anything. Then it is not getting anything. Then it is not getting anything here. So there is a gap of every 5 minutes. So what I can do here is, instead of idling, I can just basically say, okay, instead of idling, let me do all the desorption over 10 minutes so that it's not idling. I can do that for all of these things. So you see that the moment this bed is done, then the second bed is done. It goes to the second one, then it goes to the third one. It will be up to here. Then goes to the third one, then it goes to the fourth one. So you see this. It goes sequentially with the desorption. So the CO2 compressor will be happy about it. This one, actually, the best way to understand for you is to draw this in like even Excel, the way you draw the typically Gantt chart, like for your project scheduling and things like that. And when you start it, if you take this number, you just offset it by 10 minutes, 20 minutes, and you will see everything will actually align with this. So this is how you come up with really typical cycle design. But as I said, if you have got a really large number of beds, like you saw those crazy numbers that we had, right? Number of bed adsorption is 12 and 31. That one will require you to solve that problem actually, like you. Yeah, this guy, 12 and 43. That one actually tough to do it this way. I just wanted to show you the simple one, but you can read our paper there and see how all of these things are actually done. It's a little complicated, but for simple systems, you can do it. But this is important for your economic calculations. Okay, So I think it's about 12. I will stop here and see anybody has any questions for me. Yes. Oh no, the offset. This is actually to align with the cycle. It does not matter actually. So what you really need to look into is here. This portion that I put in, from here onwards, you will see that it is repeating. So it does not matter. It's basically because I do not know. So this is actually I'm trying to catch it. When you actually do it in a optimization problem, it will directly jump onto this one. I'm actually just, it's kind of my initial guess. So that is what I'm landing onto it. But what you really need is a cycle from where it is repeating, which I showed here, right? You see now how it is aligned, right? Everything will be aligned, and after that it will be all other things will actually be exactly repeating. Where you started, that is where exactly you start. You see, I'm starting with the regeneration here, and this is also starting with the regeneration. This is my cycle time, right? And if you see here, when I am here, I've spent 10 minutes into adsorption, 20 minutes into adsorption. So after 10 minutes, it has to go for the desorption. So that is what it will be happening. This is the 10 minutes here. So this is the place it will go for that. Sorry, I was using this notation. Sorry. This guy will go through this, and then after that it will go through the desorption and all of that. So if you notice, the place to think about is this guy. So where you started and the next end where you end, these two should be exactly the same. Where you finish, you are starting it back here. This guy and this guy, it should be exactly be matching. This is the standard Gantt chart that which we draw for project scheduling, but this is how I actually prepped it there. So I just quickly wanted to show that.
What are the typical temperatures? Suppose you are doing for flue gas from power plant. What are the typical temperatures for temperatures?
So it depends upon your absorbent. These ones that which we consider that can withstand up to about 150 degrees centigrade. So we actually solve an optimization problem. So 150 degree means that I do not want to go for 150 degrees C. I may do it at 100.
For desorption and for adsorption?
We come to almost close to the room temperature. Of course, it's not acceptable.
Cooling will take a lot of time.
Yes, it will actually. So that's why if you look into that MOF paper, we actually discussed that and looked into these ones. Like if you're seeing it is coming to 65, I'm not showing the regeneration temperature here, but that is why you are exactly right. If you take it to 150, that temperature itself will not only take time but also take a lot of energy. So that is why it's an optimization problem. You might actually like to desorb at 110 or 15 or 105 to reduce your penalty and the time for doing that. But yeah, it's an optimization problem.
If it is only CO2 is there, then okay, this temperature is okay. Suppose on the SO2 also is there, then we cannot reduce the temperature to not minimum temperature, only 80 something you should maintain it. Otherwise SO2, the formation will also take place. So
Yeah, that will.
the composition of the flue gas.
It depends on the composition of the flue gas. Most cases, I think SO2 is something, most of them really do not like SO2. Most of the adsorbents, again, I'm not a materials guy, but my understanding is that most of the adsorbents do not like SO2. And then the problem is that the SO2 will, if it adsorbs, it will be mixed with the CO2 when you are sending it down. It can lead to corrosion of the pipeline. So most cases there is a scrubber that takes off the SO2. It generally KOH or NaOH scrubber, and that it scrubs the SO2 before, and then only it is actually fed.
So in a power plant, the flue gas, even after all economic needs of heat recovery, is still above 100 degrees Celsius.
Right. So these ones, yeah, this one actually, a lot of these actually considers a direct scrubber before this. So even for the solvent-based capture, there is a direct scrubber first. So as you know, the direct scrubbers, when acceptable, they can give you the best temperature approach. So you spray water, that actually helps you both ways. It makes the gas saturated, especially for solvent based, it's very common. And for these ones, actually, you can actually. Right, so that means that it really depends on the adsorbent. For these ones, there is actually dehumidifier. So you first actually cool it down to the room temperature, then you separate out the water from the system before you feed it to this.
A lot of other energy calculations are there before
Absolutely.
you do a practical thing.
Absolutely, the pre-processing steps are actually important. That's why when you look into this to see the entire plant, actually, we have actually a lot of simulations that shows the entire plant. It just looking into the capture plant gives you the part of the story. Now you have to look into plant-wide system. Okay, other questions here? If not, yes.
Steam, what is entering actually the bed, it is in superheated condition, but there could be a tendency to condense within the bed lining itself, as the due to capillary actions and all. So that will instantly bring down, increase the temperature within the bed, and won't it again escalate desorption?
This is something only a mathematical model will tell you, and hoping that you are way above. So it depends upon what is the design cushion that you want to take, or margin of design that you want to take. But you are absolutely right, because what happens is that the steam that you are injecting, the partial pressure of steam actually keeps changing through the system. And of course, the temperature keeps changing. So you have to basically, if you see all our code there is a relative humidity calculations everywhere through the entire system to ensure that your relative humidity is below certain percentage, like 70, 80% or whatever design cushion you want to take. But you must take those calculations there, absolutely. So the trick is, with the moisture, always do a relative humidity calculations and ensure that that does not exceed certain value to avoid the condensation. Yeah. Anything else? Okay, very good. So we'll now break.
There is one question from online participant,
Okay.
Rajiv. So he's asking that how much energy DOE, Department of Energy, we need to dissolve in gigajoule per ton of CO2.
How much energy is needed?
To dissolve the CO2 according to DOE in gigajoule per ton.
Because of?
In gigajoule per ton.
Okay. Okay, so how much energy we need? So I think that's a good question, which I was probably planning to cover something yesterday as part of the performance, but let's discuss this mathematically here. Right. So if you look into any of these steps here, so how much energy do we need? First is the heat of desorption. So this will depend. So if you have a physical, if you have physisorption, generally 15 to 50 kilojoule per mole. If you have a chemisorption, this is generally 65 to 120, 130 kilojoule per mole. kilojoule per mole. So it depends on that one. This is the minimum heat that you must provide, plus the heat sensible heat needed to heat up the bed from end of adsorption temperature to the desorption temperature plus heat losses with the outgoing gas, which is CO2 plus H2O plus any other loss to the environment. So this is all comes from your simulation. So what you have to really think about it is that this gas that is going out, like when you use the hot water, like this is outgoing gas here, and the dissolved CO2 and nitrogen that goes out, that gas is actually taking away the heat from your system. So if it is going out at say 120 degree or 110 versus 150 degree, that is actually a heat that you are losing from the bed. You can do a heat recovery, that's a different case. But if you don't consider the heat recovery, that gas is also taking out that heat. And then the bed temperature needs to be heated up, that is the sensible heat, because I end adsorption say at 65 degree and I start the desorption at 110 degree, I need to heat up for that entire delta. And if I go to 150 degree, the delta may be very high actually. So that thing, and then any other losses to the environment, like from the wall of the vessel or anything, that needs to be taken into consideration. Okay, does that answer your question? Like if you check if but in the meantime, in the room, I will check anybody has any other clarity question. Okay. All right, looks like we're ready for the lunch. Is there lunch break or now? Lunch break, all right, okay.
Okay, everyone, we will take 1 hour break. We'll meet back at 1 p.m. for the next lecture. Here. Okay, lunch is LNC 306.
All righty, okay, thank you. It seems like, so I need
So, good afternoon everyone and welcome back to the lecture 10. So, in this lecture I will discuss about the modeling of the adsorption process so that you can understand how to model the CO2 capture. I will show what are the necessary equations. Okay, it could be the mass, momentum and energy balance equations that are required to design and optimize the packed bed adsorber. So, there are if you see, there are two types of terms and we used to classify them: pre-combustion capture and the post-combustion capture. In pre-combustion capture, we partially oxidize the fuel, the fossil fuel that we would like to burn, and it creates the CO2 and H2. The produced CO2 and H2 will be separated, okay, and the hydrogen will be used for the energy generation. That is the pre-combustion capture. Okay. Then that means before combusting the hydrogen to produce the energy, we are separating the CO2. That is a pre-combustion capture. In case of the post-combustion capture, we will burn the fossil fuel and it produces the flue gas. Along with that, CO2 will also come. So, we will install our capture setup to separate the CO2 from the rest of the gases. Okay, that is a post-combustion capture. So, in both the cases, the location of this adsorber, the packed bed adsorber will change, whether it is before and after the combustion process. Okay. So, the source to this adsorbent bed is very important, and what is the concentration of the CO2, that plays a major role in getting how much pure CO2 from the output. So, that is one of the important parameter that we need to incorporate in our model, and also we will see what are the other parameters we need to consider. So, here we can see the left side graphic that is showing the adsorber. If our feed contains two gases A and B, okay, and we would like to separate A and B, okay, we have a adsorbent, that is a solid that is packed inside the bed here, and from the other end we can see that raffinate coming, that is a pure B. That means the bed is adsorbed the gas molecule of A due to the affinity between the A and the adsorbent, the most of the A is adsorbed on the bed. So, here we can see the mass transfer zone and also how the concentration of the gas molecule A is changing with respect to time. So, as the process is proceeding, it is proceeding forward, then the concentration of A at the exit is increasing. Okay. Once the bed is saturated, then we observe the concentration of A at the exit. Okay. That is what the breakthrough we discussed in our previous lectures. When it comes to the desorption, desorption can be done multiple ways. As Dr. Debanshu discussed, we can go for thermal, external thermal source, and we can also inject the heat from outside, and or else we can use some purge like any inert gas that will disturb the interaction between adsorbent and also the adsorbate. Okay. Due to the reduction in the interaction, the gas molecules that are adsorbed in the bed will come out. Okay. That is the physics behind this purging. And also we can reduce the pressure in the bed. That is how the pressure swing adsorption works. If the gas is stored at high pressure, for example 10 bar, if we are releasing the pressure valve at the exit to the atmosphere pressure is 1 bar, okay, whatever the gas that is stored, that will come out, that is a pressure swing. And if we are supplying heat, okay, that means we are increasing the temperature, the desorption takes place by increasing the temperature, then also we can dissolve the gas that is adsorbed in the previous step. So, if we continuously doing this, okay, first adsorption and whatever the gas that is adsorbed, the desired gas that is adsorbed, we will use either purging or any of the regeneration method we will use to get the A back, and again we will feed the flue gas, okay, and to get the pure gas and also desired gas out of it. If we keep on repeating this, this is a adsorption cycle. This process is called a cycle. There are multiple ways of doing this. We have pressure swing adsorption, temperature swing adsorption, okay, and there are hybrid swing adsorptions also. In the coming lectures, we will discuss those techniques. So now we will see on this the fundamentals which you learnt from Dr. Ravi's lectures and also Dr. Debanshu's lectures, where we discussed what is the adsorption and what is the diffusion, how what type of resistances we observe in the packed beds, how those resistances would affect the final output, and also if we are considering all those various physics, okay, how many different types of mathematical models that will form, okay, various partial differential equations we will see. All those equations we will discuss in this lecture. So design of a adsorption process that requires development of a model, okay, which describes the column dynamics. So the term model representing here is a mathematical equation. In our engineering processes, we write partial differential equations that defines the physics of that process. Okay, then we call that as a model, the mathematical model that could predict the experimental behavior. Okay. So what is the dynamics of adsorption? That means how the concentration of the gas, adsorbed gas, that would change, and if it is a exothermic process, the temperature change takes place in the bed, how the temperature that is changing with respect to time, and also the pressure, okay, how the pressure will change from inlet to the exit, and also how it is changing with respect to time. Okay, all those various conditions, how it will change during the process is called the dynamics of the adsorption. So the absence of the accurate and efficient model, generally we will, if we have very accurate model, mathematical model, okay, we don't need to conduct a multiple number of experiments. Okay, one single experiment would be enough to develop a model. If we would like to design or optimize that process, we will use that model, okay, to get or generate the data. So I hope you will recognize this. So adsorption isotherms we estimate by changing the pressure. We will calculate the adsorption amounts, okay, at different temperatures, for example T1 and the T2. Okay, if I am conducting one experiment, that experiment is giving me the value of okay, if I pick one point here at temperature 1 and the pressure 1, that is the value of experimental data point. Okay, if I have a model at that same temperature and the pressure, if my model is predicting the same value that I am getting from the experiment, okay, the accurate model, that means the difference between the data points of both the model and also the experiment is almost close to the 0. Okay, then we don't need to go for this robust time consuming experiments. We can use these models to generate the data and to optimize the system. So that is the basic idea of learning the model. So the empirical design of adsorption column through experiments is very time consuming and expensive. So initially we can do some basic calculations for design. If we assume some length of the column and also the diameter of the column, and we will pick what is the size of the adsorbent that we are packing, and based on those calculations we will find what is the purity of CO2 that is coming out. Okay. If we are happy with that purity, okay, we will end that process there. But if that is not meeting the demand that we are expecting, okay, then we will modify the dimensions and we will either change the adsorbent and we will run that experiment again, okay, and till we reach our demand, we will keep on continue this. This is how the experiments work for multiple iterations. Okay. If we are having one very good model, okay, that model could predict the experimental result well, okay. In one day or 1 week we can get this results without conducting the experiments. So, what do we need to have a very good model? We need to understand the adsorption equilibria and also the kinetic parameters. You have seen the breakthrough curves, right? If we would like to model the breakthrough curve, we need very good model, kinetic model that could predict the breakthrough curve. And also we need equilibrium model that could also predict the experimental data exactly. So, these are very important parameters that we need to understand first when we are trying to design a adsorber. So, this fixed bed column, the mathematical simulations that would incorporate transport phenomena, how the mass is changing from entry to the exit, and how the pressure is changing, and this is an exothermic process. So, we are interested in temperature changes also. So, we need energy balance equation. So, all the transport phenomena is important for both adsorption and the desorption cycle. At the time of adsorption and also during the time of desorption, that is one cycle. Okay. If you would like to optimize, if you have some specific quantity of CO2 that is coming out of the bed, or what is the productivity or the purity of the CO2, okay, you can optimize various parameters or operating conditions, okay, by using this model. Okay, is that enough or should we validate our model? What is the importance of validation? Why should we validate the model? Correct. Yeah, so based on the physics, we are developing the model. Okay, once we have a result, we need to validate that with experiment, at least one experiment, okay, to get confidence that this model can be utilized for other generating the other data points, okay, for various conditions. So that is the idea. So we will verify our model with the experimental data that is available, okay. We can pick the information from the literature and we will compare our model results with the experimental results. It could be the breakthrough curve or adsorption isotherms or the performance metrics. So to predict the column dynamics, various set of coupled partial differential equations we need. We will see all those equations, various PDEs with mass, momentum and energy balance equations which must be solved. So I will go through the overview. So in this particular study, when we have a source that is a flue gas, okay, when it is in contact with the packed bed, we have gas solid phase, okay. We have two phases where CO2 will come in contact with the solid adsorbent. So the dynamics of the column requires the gas solid equilibrium, how much amount of the adsorbate that could transfer onto the adsorbent, and what is the capacity of the adsorbate that is accumulating on the adsorbent. That is that information we will get it from the gas solid equilibria. So and also the complexity of these models. So when we are taking these porous materials, porous adsorbent materials, the diffusion and the film transfer is very important. That will make our model, the mass transfer, very complex. Okay. So if it is more complex, then there are multiple calculations are required to get the accurate result. So what gas and mass transfer zone is also decided by the gas solid equilibrium. So if you remember the breakthrough curves, okay, after some point CO2 was observed at the other end. Okay, slowly it will start. Right. So this mass transfer zone is also actually depends on the gas solid equilibrium. What is the adsorption, how much amount of the affinity that is present in between the adsorbate and to the adsorbent particles. So now the first parameter we will note down, that is the adsorption equilibrium. Okay. So this is one of the parameter that we need to model the packed bed accurately. So we will go one by one, what are the various characteristics that we need to build a accurate model. So first information that we need is adsorption equilibrium. So another important point, so adsorption is an exothermic process. When we have these high concentrated flue gases, the flue gas that contains very high CO2 amount, okay, that will release the more heat. So when it is releasing more heat, the heat should distribute equally. Okay. Can we consider isothermal process in this case? Is it correct? The question, did you understand? When can we consider isothermal? Temperature is supposed to be constant. Okay. Unfortunately, we are going for the porous materials where the thermal conductivity is very poor. Okay. When the thermal conductivity is poor, so this is how our bed looks like. Okay, there are pellets which are packed. The pellets are the porous pellets. It could be the metal organic frameworks. Okay, the carbons, zeolites are coughs. So when the gas molecules are coming in contact with the adsorbents, okay, it releases the heat. The heat supposed to distribute equally. If the thermal conductivity is very good, then the heat will distribute rapidly throughout the bed, okay, then the isothermal assumption we can consider. However, due to the poor thermal conductivity, we may observe the hot spots in the bed, okay, where there is heat that is present, and this will disturb the incoming gas adsorption also. Okay, whatever the CO2 that is coming into the bed, it requires the low temperature prefers good adsorption. However, due to the hot spots, the gas would not absorb this. So to model this behavior, to understand how the temperature that would affect the adsorption amount, we need to have energy balance also. So the temperature effects are very important along with the mass balance. I hope you convinced with that physics, right? Why we need energy balance equation. So in addition to the mass transfer will tell us how much amount of the gas that is adsorbed and how much amount that is diffused in the bed, okay, and energy balance is required to understand how much heat that is generated, okay, how much that is affect the incoming adsorption. So along with that, we need to understand the axial pressure, okay. If based on the particle size, the pressure drop will be changed in the bed, okay. If the particle, if the axial pressure along the bed is increasing, we need to estimate that change in the pressure in the bed, okay, and that information we will obtain from the momentum balance. Okay, that so far we have discussed how the species balance, that is the mass balance equation, that will tell us what is the concentration of the CO2 and other species in the bed, okay, along with how much amount that is adsorbed. Then we have energy balance equation that gives us the information of the temperature, how much temperature that is accumulated, that is generated, and then we need to understand what is the pressure, how the pressure is changing inside the bed. Okay, now coming to this various length scales that are involved in this system, this is a very nice figure where the particles, the pellets are packed, okay, which are porous pellets. This adsorber that we see is in 1 meter length scale. Okay, then we have a pellets where the gas is diffusing through the voids of the pellets inside the bed, and then in the pellet we have a pores, the pores, macro pores, and also inside the particles also there are micropores. Okay. So at the particle level, okay, less than nanometer in the angstrom scale, we see how the CO2 interact with each other, and also how CO2 interact with the adsorbent. Okay, to design one or optimize adsorption process, okay, we need to understand the physics from the small scale, that is molecular level, the interactions between the adsorbent and the adsorbate, and also the mesoscale, how the gas that is diffusing through the macropores and also the mesopores. Okay, that information we will get it from the mesoscale, and also mass and energy balance in the pellets and also in the bed. Okay, this information is very important to get a accurate model. Okay. So if we carefully observe, the adsorption is happening here, okay, and gas particle will diffuse through these pores of the macro pore of this particle pellet. Then there is a micropores inside the particle, okay, and also gas is diffusing through the voids of the bed. Okay. So we will quickly see what are the things we learnt and what are the important parameters to consider for modeling this behavior. So first thing is adsorption equilibria. Okay, adsorption equilibria tells us how much amount of the gas that is adsorbed on the surface. Okay, we will consider this adsorption equilibria by using adsorption isotherm models. Okay, we will incorporate adsorption isotherm model that gives us the information how much amount of gas that is adsorbed. Then selectivity. Why selectivity is important to consider? Yeah. So there are two types of selectivity: adsorption selectivity and the diffusion selectivity. What is the difference? I have. Please. So when we are having the flue gas, okay, all of us interested from this particular topic, we are interested on CO2. Okay, rest of the gases right now we don't want those rest of the gases. We want CO2 to be stored in the bed. Okay, so when we are selecting the adsorbent, it has to be CO2 selective. Okay, if it is adsorption selective, the adsorbent must have a good interaction. Okay, strong bonding with the CO2, that is adsorption selective. If it is a diffusion selective, comparing with other rest of the gases, CO2 diffusion difference is important. Okay, other gases should come out of the bed quickly compared to the CO2, that is a diffusion selectivity. Okay, if somebody is saying that their system is adsorption selective, that means bonding of CO2 with respect to adsorbent is strong. Okay, if it is a kinetic selective, okay, that means the diffusion of the other particles are faster, which are going out of the bed quickly compared to the CO2. Okay, those are the driving forces. That's why we have a breakthrough curve and also we have adsorption equilibrium. Both are very important in modeling the behavior for CO2 capture system. Yeah, kinetics, we will get that information from the breakthrough curves. Okay, we have linear driving force models, and we have a couple of other models which will pass this information to the mass balance equation. Then heat of adsorption, we will estimate the heat of adsorption as we discussed in our previous classes. This heat of adsorption, to which balance equation we will feed this information? We have mass balance, momentum balance, energy balance, right? Where this information will be useful? Energy balance, okay. So whatever the amount of heat that is releasing, okay, that is a heat source. Heat source is a term we will use in the energy balance equation, okay, that will tell us how much heat that is releasing and how it would affect the temperature in the bed. Then again coming to the pressure drop, the pressure at the entry of the bed and also the exit of the bed are not same, okay, because there is a packing of the particles in the bed that would cause the difference in the pressure, okay. We are interested in the pressure and we would like to estimate the pressure change by momentum balance equation, okay. So now coming to this analysis, so in fixed bed column, the mathematical models predict the transient behavior of concentration and temperature profiles. We will see equations one by one, okay, then you will get a clear picture of what I am talking about. They are complex partial differential algebraic equations and which are mass, energy, momentum conservation. So also we will incorporate how the mass transfer rate, how the CO2 that is transferring from the gas phase, that is a bulk phase, to the surface, okay, and also equilibrium adsorption isotherm models will incorporate in the system, okay. That will tell us what is the capacity of these models and also the thermal effects and the pressure effects. So first starting with the fluid phase material balance, this is a equation for the fluid mass balance, okay. This contains the accumulation term, okay, that is dou Ci by dou T, and there is a axial dispersion term. When this gas that is diffusing are entering from the bed, okay, we have a convection term and also we have diffusion term, okay. This is a dispersion term and we have a convection term through the bed in the axial direction, okay. And what is this term? No, not 1 minus epsilon by epsilon, the entire term. What is this term? So the accumulation of the gas pieces due to the adsorption, okay. So if you observe, Q is the term, okay, that is the adsorption amount. The Q we will get that information from the adsorption isotherm model, okay. That adsorption isotherm we will use the model to fit the experimental information, the Excel sheet which I have shared in our previous tutorial, okay. That is your adsorption isotherm information, okay. We will fit one adsorption isotherm model to the data and we will use that model here, okay. That is how we will get that information. So there is this term axial dispersion. We can, so most of the cases we have these assumptions. We will assume a few things to simplify these partial differential equations, okay. So when we have a plug flow pattern, okay, there is a negligible axial dispersion. In that case, the convection will be, if we assume that convection is dominating, then we can ignore this second order PDE equation. So that is one way of simplifying it. Now coming to the kinetic models, the kinetic models are like a subsection in the species balance, these mass balance equations, because there is this term called dou Qi by dou T, okay. How we are getting the Q? So that is a very important information we need. So the dou Qi by dou T, we can tell that as a overall rate of mass transfer for component I at time t, okay, which is averaged, the 2 bars that you see, right, that is averaged quantity. So mass transfer kinetic models depends on assumption. We can assume that local equilibria, local mass equilibria, that means the amount of gas that is adsorbed, okay, which will be equal to the Qi bar. So this local equilibria simplifies the mass balance equations. At rapid mass transfer, So when gas is entering the feed, okay, first it will touch this solid, the porous solid pellet. Okay, the pellet is like that, which contains the pores. Before reaching the pellet, there is a film resistance. Okay. So and also there is gas that is adsorbed on the surface, okay, at the equilibria. So what this local mass equilibria assumes that there isn't any film resistance and also the diffusional resistance. I am assuming that dou q bar by dou t is directly equal to the adsorption equilibria amount, but that is not exactly correct for the real case. We will see how the dou qi double bar by dou t is equal to, and also we will consider multiple diffusional and the film resistances in between. Okay, this q star is there, right? Q star is nothing but the adsorption equilibria, the adsorption amount that we estimate from the experiments. Okay, so local equilibria is an assumption that we consider to simplify this kinetic models. Okay, where dou q I double bar by dou t is equals to dou q star by dou t. If you are considering this assumption, you are not worrying about macro pore diffusion, micro pore diffusion, and the resistances, film resistances that are coming into the picture inside the pellet. You are simply considering whatever the average of Q that is accumulating on the particle is equal to the amount that is adsorbed. So that is the simplification from this assumption. Yeah, here you have very nice picture. Okay. So when there is a gas particle that is coming here, okay, around this pellet we have a film resistance, that is the external fluid film resistance. If you recollect from Dr. Ravi's talk, okay, there is a film mass transfer coefficient also we will use. So inside this pellet we have these macro pore resistances, okay, how the gas molecule will diffuse through the pores, macro pores. Okay. Then so this pellet is formed by combination of multiple particles. Particle also contains the pore, okay, they are micropores. So micropores also contains a resistance, okay, that is a micropore resistance. So what we are trying to figure out here, in case if we are looking for a very accurate model, we need to consider micropore resistance and macropore resistance and also the film resistance. So we will look one by one closely. Okay. So mass transfer from the fluid to the solid phase occurs is the very important step. That is where the film transfer resistance we consider in the packed bed. If local equilibrium theory is reliable, okay, only for the adsorption selective systems. Okay, when can you consider the previous assumption which I made? Okay, whenever there is a adsorption selective system, there is a strong adsorption is happening, but not for the kinetic selective system. If the diffusion is playing a major role, okay, if there is a difference between the diffusion of your CO2 to the rest of the gases in that adsorbent, then you better consider all those resistances, okay, the diffusional resistance in the macropores and also the micropores. So what are these potential resistances? The external fluid film means around the particle there is a resistance, that is a film resistance, okay, that we learn in the mass transfer. And inside intraparticle diffusional resistances, in our case there are two intraparticle resistances. Okay, one is macropore diffusional resistance, that means if there is a pellet, how the gas is diffusing through the voids of the pellet, that is a macropore resistance. Then we have a micropore diffusional resistance. Micropore means the particles having the voids, having the small pores, okay, how this gas molecules is diffusing through the pores of that particle, that is a micropore diffusional resistance. Okay. So the coming to this external fluid film resistance, the concentration difference across the boundary layer surrounding the each particle will give us this film resistance. Okay. Here you can see how dou qi by dou t can be calculated as Ci, that is the concentration in the bulk phase, to the Cpi on the concentration of this gas on the adsorbent surface. Okay. So there is this term diffusional resistance. If 3 by rho Rp epsilon P dPi by dou Cp I by dou R, this is a gradient. This is a concentration gradient from the surface of this particle to the center. Okay, this also tells us the information of dou Q by dou Qi by dou T. So now we'll start with macropore first, then I will show what is the micropore resistance. Okay, so the diffusion molecules escaping from adsorbent force field during the diffusion of macro and the mesopore is called macropore diffusion. So macropore means, do you know the size of the macropores? Anyone? Yeah, greater than 50 nanometer. If it lies in between 2 to 50 nanometer, we call it meso. Okay, if the diffusion is happening in that size range, we can put that in macropore diffusion. So the gas molecules transport that depends on mean free path, okay, and the magnitude of the adsorbate molecule. So when molecule mean free path, okay, is more than the pore diameter, okay, we call that as Knudsen diffusion. Okay, Knudsen diffusion dominates the transport. So during that case, what happens? The collision between the gas molecule and the pore walls will take place. Okay. So Knudsen diffusion doesn't depend on pressure; it depends on the temperature. We can estimate the dKi, the Knudsen diffusion coefficient, by this formula, where we can see the temperature that would affect the diffusion coefficient. So this is the equation we will use to estimate the concentration of the gas, the CO2, okay, that is diffused through the macropore. Okay, this looks similar to the bed equation. However, here the accumulation inside the particle, okay, inside the pellet, and also the how much amount of the gas that is adsorbed on the micropore or the particle, okay, not on the pellet. Okay, this is again the diffusion inside the macropore. So if the molecular mean free path is smaller, okay, then the pore diameter, the bulk molecular diffusion will be dominating. Okay, that is one of the information useful. We can use the Stephen-Maxwell equation or multi-component systems or Chapman equation that can be used to estimate these coefficients. So the collisions between the molecules is also another resistance that we observe in this case. Okay, so if you would like to incorporate the macropore diffusion, okay, we can use this equation where these are the accumulation terms in the gas phase, in the adsorbed phase, okay, and the diffusion term. This is okay. This is this equation representing which location? Are you following me? So first we looked into the bed, okay. The first, the big equation I have shown, the accumulation, that is followed by convection, diffusion, and the adsorption. So that is for the bed. So this is for the pellet. Okay, inside the bed there is a pellet. Okay, we would like to find what is the concentration of the adsorbate inside the pellet also. So if we solve this equation, we will get the concentration inside the pellet. Still, this is not over because the particles that are forming the pellet also contains the pores. So that is called micropore diffusion. Okay, so the micro are the small pores which are in the range of particle size. Okay, the particle diameter is not much greater than particle diameter, which is close to the particle diameter, so that the molecules cannot escape easily. So in this case, the transport occurs by hopping, by jumping from one adsorption site to the another adsorption site. Okay. In general, intraparticle diffusion which is neglected in this type of micropore diffusion. So now what are the resistances inside the microparticle, which is one is micropore mouth, that is the opening of the micropore. Okay, inside this, okay, if for example there are particles like this, okay, this is a pore mouth. So this is another resistance that we observe in the micropores. and also distributed micropore interior resistance. Inside also there is another resistance. So if your system that is controlled by barrier resistance, then we will simply use this term K multiplied by difference between equilibrium value, equilibrium adsorption value, and the concentration that is outside this particle. Okay, that is similar to the film resistance that we have observed. And if it is dominated by interior resistance, okay, then we will consider this equation, the diffusion inside the particle. Okay, so d mu I is the micropore diffusivity. That is the equation we will use to incorporate the micropore diffusion. Okay, now you might have bored that we have multiple things to make our model very accurate. How to simplify that? Either you can go for local mass equilibria, okay, but your system is kinetic selective. Okay, then we have an option called LDF, linear driving force model. Okay, linear driving force model is very simple. That is, if we are taking dou qi by dou q star by dou t is the local mass equilibria. Instead of that, if we are considering that dou qi by dou t is equals to k multiplied by qi star, means that is the adsorption equilibrium amount. Okay, qi bar is the amount how the concentration of adsorbate that is at that point that is changing. Okay. So now interesting factor here is what is K. Okay. So how this main motivation behind developing this model is to simplify the diffusion resistance models and the film resistances that are inside these particles, intraparticle diffusional resistances. So what we did here is we combined all the three resistances into one mass transfer coefficient. Okay, the mass transfer coefficient, this is the first term, that is the film resistance, macropore resistance, micropore resistance. Everything we clubbed into one mass transfer coefficient and used it here, okay, to define dou qi by dou t, and we are calling this as a linear driving force model. Okay, there are few advanced models like QDF is also available. Okay, you can that is quadratic version of this driving force model. So with this we are completed the mass balance equation. Okay, first we looked into the packet bed, then we looked into the particle, how the mass is transferring or mass is accumulating inside the particle, inside the pellet, then followed by the particle. Okay, that completes the mass balance, how the mass that is accumulating in the system. Now coming to the important factor, that is adsorption equilibria. We have multiple adsorption isotherm models, okay, in the literature. A few I can show now. Langmuir model, very famous model. Then we have Freundlich model. We have Toth model. Toth and dual site Langmuir and Langmuir-Freundlich, these are advanced models and actually developed on the basis of Langmuir and the Freundlich models. Okay, by overcoming all the limitations that we had for Langmuir models. Okay, by overcoming the assumptions that we made while developing these models. Okay, these are very interesting models. So we will look in the coming tutorial. Okay, we will try to find these parameters. So except pressure and the temperature, okay, and also the adsorption term, so adsorption uptake term, okay, remaining all are unknowns. Okay, so now the question is how do we estimate those unknowns, okay, so that we can use this Q star in our mass balance equation. Okay, that is the estimation of these parameters we will learn in the coming tutorial. Okay. So this looks complex, but if you carefully observe, this is actually developed from the combination of Langmuir and Freundlich, where there is an exponential term that is here, the k naught multiplied by exponential of minus delta h by RT, that represents the heterogeneity of the surface. Okay. So now moving to this energy balance equation, how many energy balance equations we need? Question is straightforward. We have how many phases? 2 phases. We need 2 equations. Gas phase energy balance equation we need, and also the solid phase energy balance equation. Solid is our adsorbent. Okay, this is a exothermic process and the temperature increases and temperature changes during the adsorption. So we need to incorporate those adsorption, those temperature variations. Okay, so I will show the equation. Okay, this is a conduction term. Okay, that is followed by how the temperature changes. This is a convection term, and okay, this is a temperature accumulation, and there is the adsorbent tank. Okay, we need to consider how the temperature changing from the bulk gas phase to the tank, okay, and also the bulk gas phase to the adsorbent. Okay, these are heat convection terms that we are considering for the heat transfer between these solid to the gas phase and also the gas phase to the wall of the tank. Now coming to the solid phase energy balance equation, okay, we have this is for adsorbent. Okay, the adsorbent, how the heat temperature of the adsorbent that is changing with respect to axial direction, okay, and how the temperature changing from the gas to the surface of the adsorbent. And what is this term? That is very important term. If we remove that term, okay, we don't get accurate result. The last term. So this is heat of adsorption. Okay, how much amount of the heat that is releasing during the adsorption. Dou Qi by dou T, again going back to our kinetic model. Okay, whatever the information that we obtained from the species balance, that would connect, okay, couple this energy balance with the mass balance equation. There is one more left to estimate the pressure, that is a momentum balance equation. Okay, in bulk fluid flows through the voids of this system. Okay, we have viscous energy losses, okay, also inertia losses. So both we can consider in this equation. What is this equation called? Ergun equation. Okay, this is very famous equation to estimate the pressure drop. Okay, where we have inertial term and also the viscous term. So pressure drop is important, okay, because if the system performance mostly affected if the pressure drop is very high, okay, the performance it would reduce the working capacity also, and it would affect the productivity, recovery, and power consumption would be high if the pressure drops are very high. So in coming class, coming tutorial tomorrow, okay, we will solve this problem. This is a packed bed that we will consider. This is a zeolite 13x packed bed we will solve, where CO2 and N2 coming the source gas we will take at 298 Kelvin and 1 bar, okay, which is 1 meter length, and at initially it is at 25 degrees Celsius and 1 bar. So these are the initial inlet conditions, how much amount of the CO2 and N2. This is ideal condition, okay. We generally don't get binary components. We will have multiple other components also in flue gases. And we will consider adsorbent in the tomorrow's exercise. And the assumptions, we generally make assumptions to simplify those complex models, whatever the equations, PDEs I have shown, right. We will try to simplify them by making these assumptions. For example, axially dispersed plug flow model that will remove the dispersion term, the second order partial differential equation. Ideal gas is applicable if the temperatures and pressures are at the normal conditions. If we are going for extreme conditions, okay, we need to go for non-ideal gas. And also the linear driving force model, okay, if we are not considering this assumption, then we need to incorporate all those micropore diffusional resistances, everything we need to consider. And also either you can go for Darcy's law or Ergun's law or Navier-Stokes, okay, to get the pressure difference in the bed. Then thermal equilibria. What is this assumption called thermal equilibria? What it will do? So thermal equilibria assumption is useful if the gas phase temperature and the solid phase temperature are same in the bed. I have shown two equations for the energy balance. Okay, it will become 1 if we are considering this thermal equilibria assumption. Okay, and also there aren't any radial gradients you might have seen in the whole equations. There is no dou by dou r. Every time it is dou by dou z. Okay, that means only axial direction we are solving. We are not solving the radial direction. If you want, we can solve in the radial direction. Okay, the del term in the first mass balance equation we have seen, right? That represents in all the directions. Okay, it incorporates in the radial also. Okay, very important information. All those equations are common for adsorption and also for the reaction. For different systems, these are common. What makes the CO2 capture adsorption system different from other systems is these two terms, mass source and the heat source. Mass source is the adsorption amount that is obtained from the how much amount gas that is adsorbed. Again, it is going back to the adsorption isotherm model or adsorption isotherm. Heat source is the heat of adsorption. These are the source terms that we get from because of adsorption process. Okay. So there are very important performance metrics. These terms you will hear when you are doing this pressure swing adsorption or vacuum swing adsorption, temperature swing adsorption, are purity, recovery, and the productivity. Okay. So this purity is the fraction or percentage of desired component. Our desired component is CO2 in this case. Okay, in the product stream relative to the total components in that stream. Okay, how much amount of the CO2 coming out. Okay, that is either mass or moles of desired component in the product to the total mass or moles of the product. Okay. Then comes to the recovery, how much amount of the CO2 that we recovered. So recovery is the fraction or percentage of the desired component successfully separated or collected from the feed. Okay, that is mass or moles of desired component in the product to the how many moles or how much mass of this desired component in the feed. Okay. Then there is another term called productivity. Okay, this productivity that quantifies the desired product that is obtained per unit or unit mass per volume of the adsorbent. Okay, that is our productivity. This can be calculated by gas flow rate of the desired product to the adsorbent mass, how much amount of the adsorbent that you are using. Okay. So these are very important terms that we use in CO2 capture by using the adsorption technique. Okay. So we have 5 minutes. Do you have any questions so far? Then we will move to the tutorial session. Before moving into that, if you have any questions, we can discuss about them. So if you recollect what Dr. Debanshu was showing, all those partial differential equations, right? Those are related to the mass, momentum, and energy balance that we estimated. We have discussed now. Okay, and also from those partial differential equations are built on the fundamentals which Dr. Ravi was teaching, the breakthrough curves, adsorption isotherm models, and all those. This is a combination of both. Okay. So are there any questions from online participants? Okay, great. Tomorrow we will solve this same the example, okay, and example in the Aspen adsorption. Okay, today in this tutorial I will show how to estimate the parameters for the dual site Langmuir adsorption isotherm model. We will start from yesterday's script file, right, where we stopped that yesterday's tutorial 1. Okay everyone, so there is one concept that I could not complete in previous tutorial. Okay, so we have gone through this example, right, the script file. All of you ran this one. Did you get the area and volume in the workspace? Okay then. So the file which you have written is called the script file. Okay. So now we will see how to create a function file. So the advantage of using these function files is we can call them multiple times. For example, there is exponential function, or you have used the tan and the cos functions, right, in the command window. So someone has written the code for those files. Okay, when you are using it directly, okay, you are getting the answer for that. So similarly, you can write your own function files. If you create in the script file, just open one new script file. Okay, you can go to the MATLAB and go to the home and create one script file here. Okay. So we will see how to create a function file. So either you can open the script file, or also we have an option called function. Okay, you can click on function, it will give you the syntax. You can replace that syntax with your code. Okay, that is also fine. Okay, I will create the function file that is shown on the slides, okay, which is function y equals to my func of x. So you can write a comments here. We are writing this function file to compute the function value of 2x square minus 3x plus 1. Okay. So our input value is x. Okay, and our output value is y. If you are using this percentile, it would not take, MATLAB won't take that as a command. Okay, it will take it as a comment. So now we will write a comment. We want the answer to be saved in the y. Okay, so we will use y is equals to 2 multiplied by x square minus 3 multiplied by x plus 1 semicolon. Okay. If you want to end this, you can use end. Okay, that will end that particular function. Then save this one. Okay, always remember, save the function file where you would like to run in that same folder. Okay, and it has to be, when you are saving this file, the name of this file has to be same as the function name. Okay, it is a myfunc is the name of this function file, so I am saving it with the same name. Okay. So now go to this command window. So all of you could able to write your function file, right? Then save the function file. Don't change the name, okay, save it with the function name. You can use different names, there is no need to be use the same function name which I am using. Okay. Control S will save the file, that will work here. Okay, there is a command called CLC. If you use that, it will clear the command window. If you type clear all in the command window, that will clear the workspace. Okay, in case any previous variables are stored, clear them before. Okay, other previous history that in the command window you can clear with CLC. Okay, now go to the command window. Once you save the file, go to the command window and type the function name myfunc, the func. So if you want to give the x value, any value, okay, let's give x as 2. Okay, you can type that as myfunc of 2. Okay, that will give the answer. Okay, answer to that quadratic equation that we are trying to solve. So once you have a function file, you can call the same equation multiple times with the myfunc name wherever you want. Once you save it, you can use this myfunc multiple times. So you can try giving the different values. Okay, so what is the syntax of this function file is, we have output arguments, whatever the output you would like to print, that should come on the left hand side within that square brackets. Okay, and untitled 4 is where we need to give the function name. So whatever the function name you are giving, save always with the function name. Okay, untitled 4 is where the function name comes. Input arguments could be multiple. Okay, you can have multiple input arguments. You know, you don't need to have x always. You can have y, z, okay, and also t. That's why we have input argument 1, 2. Okay, we can represent our input arguments there on the right hand side. So now going into this, the code, output argument 1 you should represent here equals to whatever the mathematical expression you have. Okay, that contains the input argument. So if you are calling any variable, okay, the variable which you are not mentioning in the input arguments, you will get an error. It will clearly say there are missing input arguments. Okay, so always in the first line you should mention what are your independent variables, what are your dependent variables. Okay, when inside the code, the dependent variables can be written as function of independent variables. That is what this function file is representing. Okay. So now we will move to the today's tutorial. Okay, with this basic. Could everyone able to run this, right? My function, all of you got the result. When you are executing my function with any value, you don't need to take the 2, it could be any value. Anyone is having trouble? Right. Okay, use different function name, because myfunc, someone has already created that same function, so try some other name instead of this. Give another name and save this with the same name. Go to the save. Yeah. Save as. Yeah. Okay, here change it into the function name what you are using. No, it is my function, right? Not function name. Yeah. Okay. Now it will work. Yeah. Saying unrecognized.
I give some other names.
That is fine. Is correct. Go back to that folder where you save. Okay, with that basics, now we will go into the tutorial 2, that is estimation of adsorption isotherm parameters. Okay, we will try to look into the DSL, the dual site Langmuir adsorption isotherm model by using the MATLAB. Okay. So as I mentioned, the models generally which represent the physics of the system. Okay, it could be the Arrhenius equation that we are using, or the specific heat. We use the polynomial equations. Okay, all those are mathematical models. Okay, which helps us in predicting the behavior of the system. It contains the dependent variables and also the independent variables. Okay, here you can see on the right hand side, okay, there is a Arrhenius equation that is k is equals to k naught exponential of E by RT. Okay, the k naught is an unknown, okay, and the t is a independent variable. Okay, the k is a dependent variable. Similarly, if we are trying to find the specific heat capacity, okay, we can build this polynomial a plus bt plus ct square plus dt cube, where t is the independent variable, Cp is the dependent variable. So this is one mathematical model. Okay. Similarly, we have Antoine equation where logarithm of P, the vapor pressure, that is equals to A minus B by T plus C. A, B, C are the unknowns, okay, and the T is the temperature, that is the independent variable, and P sat is the dependent variable. So A, B, C unknown values, those can be estimated if we are having the information of temperature and also the pressure. Okay, we can draw a plot with temperature and the pressure, and by using that experimental data we can fit this model to the experimental data to find A, B, C. Okay. So that is called regression, okay, how we fit this model to find the unknown parameters. So how this regression works, we use this technique to connect or to fit the equations which are in the form of dots or so if this is x-axis and this is y-axis, okay, x is your independent variable, y is your dependent variable, okay, and your experimental result is this. So can you tell me which model would fit better to this? Which mathematical equation can we use? Okay. So okay, simple, any normal equation that comes to your mind is fine. It's no need to be complex curves. Straight line, good. Okay, one simple straight line we can draw. Okay, that could connect various data points that we obtain from the experiments. Okay, this is simple y equals to mx. Okay, when we fit, we will get the m value. Okay, we will if we change the m, okay, the line will move here and there, right? So now what is the optimal m? Okay, that is the problem. So our optimal m supposed to be the value which gives us less error. Okay, this is our experimental data point. Okay, this is my model predicted data point. Okay, what we will do is, to get the optimal m, we will reduce the error between our model and also the experiment and try to reach that optimal point. Okay, that is our unknown parameter m. Okay, that is what we are going to do with our isotherm model also. This method is called regression or fitting. So this is also we use for most of our chemical engineering or engineering model parameter estimations. Okay, so x1, y1 is the experimental data, where x is our independent variable, y is our dependent variable. We have multiple data points obtained from the experiment. Okay, let's assume there is one model, that is y equals to a0 plus a1x. a0 is, what is a0? a0 is intercept. Okay, if this line is drawn over here, okay, we can use a0 plus a1x. So this is a0 plus a1x. Okay, and if we fit this model with the experimental data, we will get a0 and a1 values. Okay, next time onwards, you can give any x value. Okay, once you estimate the a0 and a1, okay, any x value can be given to this model to find the y. Okay, you don't need to do the experiment. Okay, that is the idea. So now we will see the real we'll see the derivation first, then we'll move to the one example. Okay, one linear example. So as I mentioned, our aim is to find the best fitting curve. Okay, we can draw any line on these points. Okay, but what do we need? We need the best line that comes close to each and every experimental data point. Okay, that can be done by optimization. Okay, so this squares of errors, SSE, sum of squares of errors, what it does is it calculates the error at each point. Okay, this is my x1, y1. Okay, this is error 1, this is error 2, this is error 3 and error 4. At every point it will estimate the error. Okay, it will sum all those errors and we will minimize that sum of squares of errors. Okay, that's how we will reach the optimal point. Okay, so we represent this as f of x comma theta. Here y is our output, x is the input. Okay, theta is the parameter, the unknown parameters that we use to model the information. So EI is the error, that is the difference between how much model is predicting, how much value experiment is given. Okay. So I will quickly go through this derivation so that you will be familiar with what I am talking about. Okay. Okay, let us assume there is one model. Okay, let us assume our isotherm model is the function. Okay, that is the y. Y is our adsorption amount. Okay, f of x, x is, let us assume, temperature. Okay, or the pressure. Okay, this theta could be some k or q naught, the various parameters, unknown parameters we have in the isotherm model, that we would like to estimate. So what is the actual data? Actual data is the Excel sheet which I shared, the temperature, pressure and the adsorption amount. That is your experimental data. So if I substitute some parameters, this model will predict the adsorption amount. You have already adsorption amount taken from the experiment. What we will do? We will compare at each point, at each temperature and pressure, what is the model predicted value. Okay, that value you will compare with your third column shared in your Excel sheet. Okay, that gives the error. So this error we will optimize. Okay, we will optimize this error and estimate the A0 and A1. Okay, this is example calculated for y equals to A0 plus A1x. So how we will do that? Okay, this is initially the error is yi, that is yi is the model and minus A0 plus A1x is the, sorry, yi is the experimental, A0 minus A1x is the model. Okay, the difference we will differentiate. First order differentiation gives us the minimum point. Okay, the minimum point with respect to A0 and also with respect to A1. Okay, when you have two unknowns, you have two equations, we will solve them, we will get A0 and A1. Okay, that is the solution for this. So if you get A0 and A1, next time onwards, if you give the input x0, it will calculate the y values. Okay, that is the task here. Now we will solve this equation. So in this problem, this is a problem about specific heat data of methane, okay, which is given in this table. So we are not complicating this. We have only this is not a polynomial. This is a simple a plus bt. Okay, that is a linear equation. Okay, if you want more accurate, you can go for higher order polynomials also. First, start with linear straight line. Okay, this Cp values are obtained in the range of 298 Kelvin to the 500 Kelvin. Okay, at each temperature we have a specific heat capacity. So this is a experimental information. Now the question is how to obtain A and B. Okay, so the thing is we can use the same method, the sum square of errors. Okay, and then we will obtain two equations, that is equation 1. N is the length of the array. Okay, the length of how many number of data points that are present in the table. So then this equation is actually obtained from A0 and A1 that we obtained. Okay, that is from the derivation. Now we will see in the MATLAB how to solve this equation. Okay, we will start with simple linear model, then we will move to the nonlinear equation. And are there any functions in MATLAB that are useful to estimate them directly instead of doing these derivation based estimations? Okay. So now going back to the MATLAB screen, okay, what is the first task we need to do? Okay, but we need data first, right? Earlier I gave data to you in Excel sheet. Now you need to create your own data. So the Cp and T is a matrix, or T and Cp are separate vectors, row vectors. Okay, you can create two row vectors, T and Cp. Do that first.
we have to type it, right? This is not there in the Excel sheet.
So the data is not given in the Excel sheet. This is different example. Okay, you need to open some separate script file. Okay, save that script file on the name of specific heat capacity or any name you would like to save. Okay, then create these two row vectors for the temperature and the specific heat capacity separately. Okay. Don't use the command window. Okay, use the separate script files.
I don't know the but
No, this is correct. So I sent you this presentation. Okay, you can open in your own PCs and see the problem. Okay, in the meantime, I will show that in the MATLAB window, so it will be easy for you to understand. Otherwise, you can just follow me, and while looking at the presentation. So first we can open the script file, new script file. Every time when you are opening new script file, save the script file. Okay. So in this problem, if we want to estimate the A and B, that is Cp is equals to A plus Bt, okay, we have two equations. When we have two equations and two unknowns, we can write that into the matrix form. Okay, this is very simple matrix. Okay, so we have A plus Bt. Our Cp is the sum of Cpi, all the data points that are present in the specific heat capacity, which is equals to. So if we add all those errors, right, we have n data points. Okay, n data points, that is sum of all the data points, that is n. Okay, then we have sum of xi. Xi is nothing but the temperature. So all the temperatures that we will add, and we need two equations. We have two unknown parameters here. So we have another equation that is obtained as xi yi Cpi multiplied by Ti, sum of. Okay, then A of xi, that is A is unknown. Okay, xi is nothing but Ti plus B multiplied by xi square. Okay, that is Ti square. So these two equations we will simply write that in the matrix format, that is sigma of Cpi multiplied by Ti is equals to n sigma of Ti, okay, sigma of Ti Ti square, okay, that is multiplied by AB. Okay, A and B are the unknowns. So to find A and B, okay, we can take this matrix this side, other side. What it will become when we bring this other side? Inverse. So we discussed how to estimate the inverse also in the previous tutorial. Cpi Ti, okay. So this will give both unknowns A and B. So to do that, first we need to assign what is the T and what is the specific heat capacity, temperature and the specific heat capacity.
I think the built-in function of qualified will do the same thing.
So we'll first take temperature. The temperature values are given in your presentation, you can use 325, 350, 375, 400, 425, 450, 475, 500. $35.64, that is the specific heat capacity. 36.69, 37.85, 39.13, 40.63, 41.93, 43.39, 44.87, 46.63. Okay. Now you can run and check whether the values are correct or not. You can go to the workspace and double click on this. It will give you the values that are stored in temperature and also the specific heat capacity. Okay. So now coming back to this equation. Okay. So we need A and B. Okay, this A and B can be estimated as inverse of this matrix and the Y matrix. I will take the 2 by 2 matrix as X. We will build the matrix. So the first value of this X is n. So to get the n, we have a command called length of a vector in MATLAB. Okay, that will tell how many number of data points that are present. Okay, that is the first element. Then we have a second element, second column, first row, that is temperature, summation of all the temperature points. Okay, we have a command called SUM that will give us the summation of all those data points. Okay, so the first row is completed. Now we will move to the second row. We will use the semicolon here, then it will take us to the second row. Okay, second row we have again the sigma of Ti, that is the sum of Ti. Okay, then we will use comma to go to the next column. Okay, that is sum of Ti square. So in MATLAB, if we are using that symbol dot in front of these mathematical operations, okay, it will do the array operation. Array operation in the sense, okay, there is a temperature starting from 298, 325, 350. If we are writing this as T square, okay, it would not estimate the square of the temperatures. If we are using dot power, okay, it will calculate the 298 square first, then it will move to the 325 square, to the 350 square, and when we are using the sum command, okay, it will add all those values. So once this is completed, we have Y values also, that is sum of CPI Okay, once sum of CPI is done, we will move to the next row by using the semicolon. Here also we need to use the array operation where Cp should be multiplied with the first element of the Cp will be multiplied with the first element of the temperature. Okay. Similarly, the second element of the temperature should be multiplied with second element of the Cp. Okay. If you are using the dot before the multiplication symbol, okay, it will do the array operation, elemental operation, where first element will be multiplied with the first element, second element will be multiplied with the second element. Okay. So we built both the matrix. Okay, that is this is x, this is y. Okay. Once this is done, now to estimate a and b, we can use inverse of x multiplied by y. Okay, that is the answer. Okay, so our answer is 18.9 and also 0.0546. Okay, that is the A and B values that we obtained for this system for the temperature and the specific heat capacities. So the answer for this problem is, what is the answer?
The constant is 80.91.
Yeah.
Intercept is slope is intercept is 80.91. Slope is 0.0566.
Yes. So we can, instead of using this matrix operation, okay, once you derive, you will get two equations. Those equations can be converted into the matrix form and solve it. Okay, that is one way of doing it. In MATLAB, if we have most of the cases our equations are non-linear and complicated, every time we cannot go for this method. Okay, MATLAB we have LSQ curve fit, okay, least square curve fitting function. Okay, by using this function also we can get the answer. However, if you observe carefully, for this we need one function. Okay, just now we have seen how to create a function file, right? In this example, we need to create a function file for Cp is equals to a plus bt. Okay, and also to execute this function file, we need T0. You need to provide some initial guess. Okay, for the algorithm to start the process. Okay, first one A and B initial guess should be provided, and also X data. What is our X data? Temperature. What is the Y data? Cp. Okay, everything we have, you need to create only the function file, and what the function file that you created, you should call here. Okay, and execute this particular command that will give you the answer for A and B. So we will try this. This is very interesting and it will be very useful when you are trying to estimate the parameters for advanced isotherm models. So I will switch to the MATLAB. If you want this slide, I had shared the slides with you. You can open that. So first we will write one small font.
Sir, I had a doubt.
I had shared the slides with you. You can open that. Yes, please go on.
Yeah. Yes, sir. So how do we get the normal equations for A and B? Sir?
So in the slide, okay, the sum of square of errors slide, you can see. I will just switch to that slide. Here you can see how we estimated the values of A0 and A1, right?
Yes, sir.
Okay, first we will find the sum of square of errors equation, then we will differentiate that equation with the parameters, the unknown parameters that we are trying to find. Okay, by solving
Yes, sir.
those parameters, we will get that equation.
Okay, sir.
Okay, fine.
Yeah.
Okay, first we will create one function file. You can open separate function file, or else you can write this function at the bottom of your script file. Okay, both will work. So this function file should contain the parameters. The initial values is one of the input, and also the independent variable. What is our independent variable? In our case, the temperature is the independent variable that we need to provide. Okay, now we can directly write CPM, that is equals to, so phi is the phi is a vector, the column vector that contains two rows. Okay, each row contains each parameter. So parameter A is the first row first element, parameter B is the second row first element. Okay, so when I am representing phi of 1, what I am representing here? So phi is nothing but this A comma B. Okay, A in the first row first column and B in the second row first column. This is the phi. Okay, I want to represent entire column vector okay, with the single name. That's why I am using phi. When I am writing phi of 1, that means I am talking about A. When I am writing phi of 2, I am talking about B. If I have 1000 values here, okay, I will easily represent that with phi of 1 to 1000. Okay, that is the advantage with this. Every time we cannot represent with A, B, C, D. Okay. So phi of 1 means A plus phi of 2, that is a B multiplied by T. Okay, this is our function. Okay, our function is completed. So now going back to this, going back to our syntax of LSQ curve fit. So first we need to use what are the inputs that we are providing to the function, that is phi and also the t. Phi is the initial guess we are giving. Okay, then we need to mention the function name, that is cfit phi comma t. Okay, then we need to provide what is the initial guess. I am taking 1 and 1. Okay, initial guess for A and B both are 1 I am taking. Okay, according to the syntax, now we need to give x data. What is our x? That is the independent variable temperature. Okay, then we need to provide y data, that is specific heat capacity Cp. Okay, now save this one. So you can write a separate function file also for this, and if you call that function here, okay, it should run. In the command window also you can run this LSQ curve fit. Okay, once you click on run, you can see the answer in your workspace. So your phi 1 and phi 2 both should be same. Okay. So the code for this function file and also the phi value which we calculated by matrix operation, that is given in the slide number 9. Okay, if you are having any doubt in the comments also, you can repeat those comments that are given in the slide number 9. So is it clear? Should we move to the next model? So next model is nothing but dual site Langmuir model. So by using,
Sir, I had it out.
yes, please go on. Hello? Yeah, Manjunath, please go on. Hello, am I audible?
Hello, sir.
Yes, yes, please go on. What is your doubt?
Sir, I had it out in the L square bit.
Okay, what is it? Hello, Manjunath, what is your doubt? Yeah,
So what is the value of phi, sir? Is it A and B?
yes.
So the unknown, the parameters, is that the value of phi, the matrix?
So the phi is, I am representing both A and B, the unknowns, unknown colon vector, I am representing it with the
What
phi.
is the value of phi, sir? Is it A and B?
Yes.
So the unknown, the parameters, is that the value of phi, the matrix?
So the phi is, I am representing both A and B, the unknowns, unknown column vector, I am representing it with the
What
phi.
is the value of phi, sir? Is it A?
Okay, Manjunath, it is clear, I guess.
Yes, sir. It's clear.
Okay, okay, fine. So we will move to the next example, that is estimation of the dual site Langmuir model parameters. So all of you understood how to estimate the unknown parameters for the specific capacity, right? That is a linear equation. We can estimate that by using the matrix operation or by using the least square fitting, that is LSQ curve fit. So this is a dual site Langmuir model, okay, that is one of the advanced adsorption isotherm model we use for most of the carbon dioxide capture systems. Okay, this is one of the accurate model. So here you can see there are IP1, IP2, 3, 4, these are unknown parameters. Why we have this term 1 and term 2? Because there are two sites. We consider two adsorption sites. Okay, each site will have its own energies, that is a delta H, that is represented in IP2 and IP6. And what is the input information that we are feeding to the system is, that is the temperature and also the pressure. At each temperature and the pressure we will get different Q. Okay. So the experimental, yeah. Okay, this is how adsorption isotherms look like, okay, where the pressure, with respect to pressure, the adsorption amount that changes at different temperatures from 10 degrees to 180 degrees. Okay, the left hand side is the plot for CO2, right hand side is plot for N2. Okay, these dotted lines are the experimental data points. Okay, the Excel sheet that shared is the information extracted from these figures. Okay, the first column representing the pressure, the second column representing the temperature, and with respect to the adsorption amount of the CO2. Okay. So what we will do now is, this is a sum square of errors. Okay, that is what is the value that Q model estimate, and what is the value that experimentally we obtained. It will compare the sum square of errors. Okay, when we feed the initial guess to this model, it will start from that point. Okay, it will end at the optimal point, minimum point. Okay. So now how we will do this? First we will create one function file. Similarly, the function file that we created for CP, the CP is equals to A plus BT. Here we will create a function file for the dual site Langmuir isotherm model. Okay. So before that, we built one matrix, right? Two row vectors for temperature and the specific heat capacity. So what are the values we need in this case? What are the dependent variables? What are the independent variables? So our Q is the dependent variable. Okay, we have temperature and the pressure are the independent variables. Okay, we want that information, that is the first information. First two lines of your previous code, right? Cp equals to A plus Bt. We have started with T and the Cp. Okay, so how do you get the P and T and Q in this case? Yeah, I shared with you the data. Okay, first you need to load the data. If you use this command, everyone, you can open new script files. Okay, once you save your previous files, just open the new script file. Okay, and give this command, and everyone put that Excel sheet. Okay, today also I had shared one Excel sheet with only 283 Kelvin isotherm. Okay, yesterday I had shared 227 data points. Okay, today we have only 50 data points, only 283 Kelvin isotherm. Okay, let's figure it out, only one isotherm. Okay, later you can do the exercise of fitting to all the isotherms. So today I sent you one Excel file, download it and put it in the same folder where you are running the MATLAB. So first command what you need to give is this data is equals to XLS read. Okay, that will open the Excel file and read the three columns starting from the column 1 to the elements that are present in the 50th row of the column C. Okay, the third column. Okay, if you can see the data in your workspace, then start loading those information into each column vectors. For example, if you have the temperature, that is your first column, okay, extract all that information from the data into the temperature. Okay, similarly have the pressure and also the adsorption amount into 3 separate vectors. Okay, this is how you can load that information. Okay, the pressure is in bars, that's why I converted into the pascals. Okay, to do that we can multiply that with 10 power 5. So anybody is having trouble in loading the data? No, that is the first step. Let me know in case if you could not load the data now. Okay, I will switch to the MATLAB so that we'll see. So the first step is write one function file. Okay, we will build a function file to the adsorption isotherm model. Okay, our output is n adsorption or the Q. You can pick any one. We'll take capital Q. Okay, and this is a dual side Langmuir model. We will use the function name DSL. Okay, and first in previous example we mentioned phi, right? Similar to the phi, here we have six unknown parameters. Okay, which we will represent with either phi or the variables. I am writing it as VAR. Then we need to give a x data. Okay, x information is the pressure here. So now I will load this information. So I have saved yesterday's file, so that's why I am loading the same CO2 N2 and extracting only 283 Kelvin. Okay, 283 Kelvin present in between 187 and the 226 rows. So now we will define the variables that we have, that is VAR1. Okay, VAR1 is our IP1 and IP2, that is VAR2 variable 2, and I3, that is our variable 3, I4, variable 4, okay, whatever the initial values that we are giving are the inputs of the variables. Okay, those variables will be assigned into each parameter, that is I1, I2, I3 up to I6. Our dual site Langmuir contains 6 unknown parameters. So once you load the information, you can assign that information by this. Our pressure is the first column. Okay, all the rows we need in the first column, which is converting into the pascals. Okay, that's why we have bars that are multiplied by 10 power 5, and to extract the temperature, that is the second column, we will assign that into the T, capital T. Okay, now we will write a formula for the Q, that is a dual site Langmuir formula. So there is a universal gas constant we need to provide, capital R. Okay. So now we have I1, that is multiplied with I2 exponential of minus I3 by T So this completes the first term. So the first term representing the site 1 and the second term representing the site 2 in the dual site Langmuir adsorption isotope model. So it starts with I4, I5, I6. So once you load the information, you can cross check whether it is loaded or not. Okay, you can evaluate that in the command window by right clicking on here. Okay, it is showing that unable to open CON2. Okay, because there is a 2 missing here. Okay, this information is loaded. We can check the pressure and temperature also.
I think you have given the opposite columns. First column is temperature, second column is pressure.
Okay. Yeah, first column is temperature, second column is the pressure, and third column is the adsorption amount. Okay, so this completes the function. Okay, once this is done, then half of the job is over. Now we need to go back to the LSQ curve fit, the syntax. We need a function file, we need an initial guess and the x and y values. That is enough. So function value is already defined. We can save this with a DSL. So LSQ curve fit can be written in this form, okay, where the residual norms and also the exit flags, where the algorithm is coming out, the number of iterations, and also what is the output of that gradient, that also can be obtained, and what is the value of x. Okay, if you are not specifying this syntax, then you will get only the x value. Okay, x value will be stored. So what are the inputs we need? We need to represent the function name DSL that we created, and also what is the initial value for all those unknown parameters I1 to I6. Then what is the x data, the pressure, and what is the y data, that is the adsorption amount, and what is the lower bounds and upper bounds also we can specify within the range, what range we want these parameters will be. If you have very good idea about the physics of your system, or you can do small research by going through the literature. Okay, the information that is already present in the literature would help you in fixing these boundaries under what is the lower bound, what is the upper bound. Otherwise it will go through the entire space, okay, to find the value of the x. Okay, that's why we will use the initial guess and try to execute this. So it is clear so far, right? Or you want me to wait for some time? So now going back to this LSQ curve, once you built your own function file for the adsorption isotherm model, okay, we need to represent that function here, that is DSL, yeah, DSL variable comma p, okay, that is followed by the what is the initial guess that we are giving, okay. I have given one initial guess here, which is this guess is obtained from the literature, okay. From the literature we got some values for the parameters of CO2 adsorption on zeolite 13x. So then we need to provide what are the x and y information, the small p, and also the adsorption, okay, the adsorption amount.
If we are passing the p through parameter, why are we reading the file again and overwriting that same?
Where? Inside the function. Function is independent, where you can use it later also. If you are if you are creating one separate function file, okay. I'm just putting that for my convenience to show the both script and function file together. Okay, you can have separate function file where p and t everything is given. Okay, or else you can use p and t as a inputs to be provided. Every time you need to provide different p and pressure and temperatures. Okay, once we have the x data, then we need to provide what is the y data. Okay, y information is the column 3. We will take that as an experimental. Okay, that is the data that is obtained from the column 3. Okay, and I can give the boundaries, lower boundaries and upper boundaries, where the parameters are varying. Okay, the I1 to the I6, the values that are changing from lower bound to the upper bound. So there is an error. It is saying that local function name must be different from the script file. So error saying that function value and the y data sizes are not equal. So the y data that we are taking, okay, it is an experimental, that is 40 by 1, and the x data, that is pressure, okay, that is also 40 by 1. So if you click the x value that is given in the workspace, okay, that is the value of all the parameters that we are trying to find: I1, I2, I3, I4, I6. So if you are confused with selecting the initial guess, okay, you can refer the literature how to select what is the various unknown parameters based on either the Langmuir parameter models or the Freundlich models. The information that is already available from the previous literature, that range can be selected, the lower bounds and upper bounds. Within that range, it will try to estimate the parameters. Okay. Here first we created one function file for dual site Langmuir model, okay, similar to the specific heat capacity. We created one function file, okay. Then we use this LSQ curve fit, okay, the linear square curve fit model, where DSL is called here, the function file, okay, and we used variables, the variables initial guess, VAR is the initial guess, okay, that initial guess is specified here, and P, small p is the input, the pressure that is obtained from the experimental information that is provided here, and also N experimental is the adsorption amount from the Excel sheet, that is the experiment obtained from the Excel sheet, that is followed by lower and upper bounds of the parameters, unknown parameters, okay. That gives us this x is the optimal value, okay, optimal parameters of this adsorption isotherm model that we would like to estimate. So we can verify whether these parameters can fit well or not with the experimental data. So first try writing a code for this, okay, and execute the x value. So then once we have x value, this x value can be substituted in this equation, okay, and compare this equation with N experimental, okay. Then you will get very nice plots like this. Okay, so the dashed line is the isotherm model, okay, and the dotted line is the this circles is the experimental data, okay. If your fit is very good, okay, and then your dash line will come on the top of this experimental data. Otherwise you will see the error between these two lines, the line and the circles. That is how we can verify whether our parameters are correct or not. So the code for this also given in the slides, in case if you would like to go through that. So everyone please try and practice this problem. Okay, we will discuss this in the coming tutorials or after the research seminar. So at 4 we have research seminar in room number 311. Dr. Debanshu will present his research work and also he would like to interact with you in case if you have any discussion regarding your research work. Okay, we'll meet again. After the research seminar, we will have lectures tomorrow morning by Dr. Debanshu. Dr. Debanshu Bhattacharya. So he's working at West Virginia, US. He is expert of process simulations, optimization, and artificial intelligence and machine learning in the energy systems. So today he will present his research work that happening in his research group, and you can interact after the research talk. And if you would like to discuss on any of your research problems, he will be available. Yeah. Thank you. Please.
Okay. Yeah. Should I use this one? Is this one picks up better? This one is good? All right, okay. I'll be using this. The microphone will really help me. It seems like my voice is giving up at some point of time. Got something there. Okay. So thanks everybody for attending the seminar here. What I'm actually going to, that's the thing here. Let me see if I get it here. Okay, all right. So that way I'll be standing here and can give the presentation. Okay, so I'll be talking mainly about some of the work that which we have been working over the last couple of years. So many of you who are attending the workshop here, we have been focusing on the adsorption-based techniques. This one actually will be talking about a systems level perspective, like basically saying how to take the capture system is only one piece of the puzzle, right? As I keep saying there, so question is where does it fit in? What else we need to consider? So that aspect here. So before I go forward, I would like to talk a little bit about the university campus. It's actually located very beautifully near near the river over here. So we call it a Mon River. It goes to all the way up to Pittsburgh, and there are 3 rivers that actually connect there in Pittsburgh, and all of them go all the way down to the Gulf of Mexico. Okay, and our campus is like engineering campus is here. So this big building is actually our basketball court, and then the downtown campus is here. So this tall building is actually the engineering building. This is actually the building during all these things during the fall colors. This is the downtown campus. You cannot see the engineering campus here. So these buildings are actually these buildings here. But during fall colors, and it's actually very beautiful. There is a lot of resemblance with Vishakhapatnam here because of all the hills. We do not have the ocean, but it's actually very hilly, and you get a very nice view even from our offices there, and everywhere you see it's actually open and wonderful. And the weather is actually also very nice. That's what we really like it. Very moderate weather all through the year. We get snowfall, but summer is actually very pleasant. Like 20-25 degrees C is the max during summer, and if it heats up, it will rain. 2 or 3 days, if it heats up, it will rain actually. So it's a really like that one. We have a very short growing season for any agricultural thing. So my wife is very interested in growing all the vegetables, but we always spend like hundreds of dollars, but really get nothing because it's only 2 months when the temperature will go up, and then it's almost like seems like the fruits are coming, and then it will actually go down because the temperature can go to 0 degree at any point of time. If it rains, even in summer, if it rains, it can go to 0 immediately, like in a couple of hours of rain. So, but really, overall, it's very beautiful. What I'll be talking about, one thing that worries us always, that all these beautiful art, will we have these beautiful art for our next generation, right? So all the global emissions and the greenhouse gas related issues and global warming, where does it lead us to, like even in the future, right? Should we be able to maintain the earth as beautiful it is, or be destroying a lot of those things? So here this is a pretty big topic, right? But out of that, I'm just really focusing on 2 things. One is centralized power production. So in India, mostly what we have is centralized power production. I'll also be talking about the distributed power production, and that I will explain when I go there. But the question is how you do the decarbonization of that. And then also I had a little bit of a distraction here is in terms of showing some of the work with artificial intelligence, machine learning, what we can do in decarbonization space. So first thing I would like to do is the centralized power production. So for this is a work that which we did with Linde, and as many of you may be knowing, Linde is a very big company in the space of air separations technology, hydrogen generation technology, and all of those things. And one thought that they were actually having that as part of their hydrogen business, can the power plants, when actually you have a lot of solar and the wind and the renewables there, can the power plant actually utilize the excess power to produce hydrogen? And you store that hydrogen and utilize that hydrogen during the night time when you do not have the solar power, or maybe the wind will be going. This concept can work out even for a seasonal storage, and we have looked into that also, like basically saying during summer you produce a lot of hydrogen, and then during winter you actually utilize it. Because this is one of the biggest thing here is that going to renewables does not really solve your problem, because question is how do you power everything during the night, right? So this is the aspect that what we wanted to look into. So the concept here is the following. So this is the natural gas combined cycle power plant. So there's a gas turbine, and this is all the systems over there, and this is the turbines and the gas turbine producing power. So what is happening here is that when you have excess power, what people are doing there is that they cut down the load. So I'm not sure about the operations here in India, but in the US, lot of power plants actually do something called a two shifting. So during the night time, like after 5 or 6, they will crank up the power, but during the daytime, they actually reduce their power to minimum, or they will even shut down. Because there is no demand for this, because this is so much of renewables on the grid, and people have put up the renewables on their rooftop and everywhere, and everybody is putting power to the grid, and you provide all of those things. So what happens to this excess power? These power plants go down all the way to their minimum load, and during the night time, evening time, when the solar goes down, it will crank up. So the question is, instead of doing that, like going up and cycling, can you use that excess power through an electrolyzer, put in a hydrogen storage, and you then inject it along with maybe the natural gas or by itself to the gas turbine. And this is your overall capture plant, and you do also the compression. So the point here is that when you try to consider these, you just cannot only focus on this part. You have to consider how the plant is operating here, how this is operating here, as well as the CO2 compression system. So this holistic thing is the aspect that you have to consider. Now, if you go with the technology to somebody and that guy will immediately say, well, seems like a good idea. Can you tell me what should be the rating of my electrolyzer? Should I buy a 1 megawatt electrolyzer, 5 megawatt electrolyzer, 100 megawatt electrolyzer? How do you tell me that what should be the electrolyzer power? Because that costs actually a lot of money. It also can ask you what should be the design capacity of the capture unit. How do you decide what should be the capacity of it? Because this plant is cycling up and down, so how do you come up with that? So this actually requires you not to consider a steady state problem, because the overall system is unsteady. You have to consider the seasonal variation. Like for example, here right now, it's a very moderate or reasonable temperature here, but I'm sure that in a month from now, this will not be the case, right? So then you will crank up the air conditioning and all of that thing, and in the winter, you may not need anything here, right? So question is, if I actually put money on ground, I cannot just put the money on the ground and it gives me nothing for 9 months in a year. So how do I come up with that? So that considerations needs to be there. So we pose it as a dynamic optimization problem. So I'm sure that everybody in the chemical engineering space is familiar with the NPV. It's the net present value. So net present value actually takes into account the capital cost and the operating cost and the time value of money, right? The money today is not the same as, like 10,000 rupees is not the same as 10,000 rupees 10 years from now. The 10,000 rupees will probably not be like even 1,000 rupees 10 years from now. So the time value of money is something which is important. So you need to consider that. And then we consider a bunch of models over here. These models are steady state we consider only because their dynamics is very fast. So this is the CO2 compression. Compression models are very fast. The TEG absorber, this is actually for dehydration of CO2 before sending it to the pipeline. Then we have the electrolyzer and the hydrogen compression. These are actually generally very fast model. Then we have the dynamic model of that solvent-based capture. That solvent technology that we are considering is the Linde BASF technology. That's a proprietary solvent that which we consider. This is a very detailed dynamic model that which we have as part of that. And then also we have the dynamics of hydrogen storage. I will show you why we need to consider the dynamics of the hydrogen storage. Also, we have the natural gas combined cycle plant model there. And that natural gas combined cycle plant is, we developed over last couple of years and validated with bunch of plant data and all of those. So that's the model that which we are using there. So how does it look like? We have the revenue, and you notice that we are making decisions every hour, 24 hours, and then for 365 days. So every hour for 365 days. So that's what we are considering. And right now we are considering every year is the same. but we have other projects also where we have a variation from year to year. But this result that I'm showing you is basically saying the plant life is 30 years, but I'm assuming here that all the years are basically the same. And then this is considered all the net power, and this is the operating cost here, and this is basically some equation that brings it back to the current value for the NPV calculation, and this is the capital expenses calculation as a function of the design variables. Okay, so once you have that, I'll quickly go to what we are trying to do. So in the US, every region is divided by something called an ISO. So these ISOs actually manage the power flow in that particular section, and they are connected to each other, right? So that is how the national grid is developed, but each ISO has a jurisdiction. They actually set the price for that. They manage the power in that section, okay? And you can be a private person, and you can make a contract with the ISO, and you basically say, yeah, I will be sending you power whenever I have, or whatever. Or I am putting a 100 megawatt power plant, I will be sending it to the grid. ISO must be, you must have a contract with the ISO. That will basically tell you that, yes, I will be taking your power and you are good to go, and you will get the money because of that. So that's how it is. So there are two ISOs that I will be mainly talking about. One is the California ISO. So as many of you who are in the talk in my workshop here, I mentioned to you before that California is one of the interesting one, because they have, like last year, they had 60% renewable. So California's power demand is almost about 1/5 of that in India. So that's just a single state. They have a massive power demand, which is right now is almost like, if you take the average power demand in India, it's about 1/5, 1/4 around that. And 60% of that is in renewables actually. So they have a lot of fluctuation in the thing. So if you look into the price over here, you see that many times they run into zero. Actually, sometimes they go into negative value. So if you want to put the power in the grid, you have to pay money to the grid operator, because they basically say, I don't need your power. If you make the power, I have to waste the power somewhere, because so much renewables and so much sun coming there, and then you basically have you don't have that much of a demand. They will give you $0 actually. That's how it is, goes there. And then at certain point of time, you will see that it will pick up here. This is $1 per megawatt hour. This is maybe in a winter day, or sometimes where there is no solar and you suddenly require a lot of power there, and that is when it go up. But it actually fluctuates quite a bit there. And then there are a bunch of other cases. Here we worked with two organizations. One is the National Renewable Energy Laboratory. This is one of the US Department of Energy laboratory, and also with the Princeton University. These are all predicted price with considering different type of carbon tax scenarios. This is $150 per ton and $100 per ton. So when you say 150, that basically means it's considering $150 per ton, and 100 means the same California ISO considering $100 per ton. Okay, so now coming to this, what it shows you is that these are, by the color coding, it shows you what is the optimization variables in terms of operation, and then these other color shows you what is the design variable. Now the point you have to remember here, this operating optimization variable, that what you are seeing here, like the hydrogen flow rate, this one, this one, this one, all of these, we are making a decision for every hour for 365 days. So it becomes actually very gigantic dynamic optimization problem. So we consider three different cases. So that LMP data that I will actually talking about, these are the LMP data. So this is known as the locational marginal price. So that basically means is that the price at which you will be actually buying the electricity from, you will be selling the electricity to the grid. So that's what is that LMP that actually stands for. So now let's see what we find. So first case is NGCC only. You basically say, I'm not going to do anything. I just sit tight here. I have an NGCC plant, business as usual. What happens? Okay. Second scenario is I have NGCC and just have a capture plant I add, that case 2. Case 3 is our proposed system, which has got NGCC capture plant, but I also add an electrolyzer which is producing hydrogen and providing you with that power. So what happens to that? I already mentioned about the design and operating decision variables, and this one we optimized in PyMO, and because this is actually, as I was telling, these are dynamic optimization, large scale. We can have as high as 2.5 million equality constant here, okay? So, and all these number of decision variables that we need to really optimize here. So let's see what is the result. So first, once the consideration we have is hydrogen storage in the vessel, and you see KISO 150. If you notice here that just particularly notice the NPV values over here. You see that case 2 has got a higher NPV than case 1, so that means it is more economically favorable. And case 3, the proposed case, is even more economically favorable. So it is saying having that integrated system of hydrogen generation is really helpful. Another thing you will have to see here is this plant utilization. Plant utilization basically means is that if you just think about business as usual, you will be only operating 39% of the time. So 60% of the time the plant is shut down because you are not making money, you are losing money, so it will shut you down. But if you do the optimization, then it actually increases to up to 56 or 58%. This gives you the electrolyzer capacity and utilization and CO2 capture, plant capacity, and all of that thing. So it actually says the case 3 is profitable. Then we consider the hydrogen storage in cavern. So these caverns, again, I'm not sure how many of you are familiar with this. These are some new concepts, I will say new concept. It's actually kind of a little older concept. People use this cavern for other purposes. These are being repurposed for storing hydrogen. These are actually salt caverns. So what is their capacity? This is the capacity. So this is 300 million meter cube. So as I was saying that other day, that many parts of the US, they have already identified and they have already formed these salt caverns actually, where you can actually, under those caverns, you can securely store hydrogen. No issue about actually leakage of the hydrogen. This is tested and verified. So the question is that if you do a seasonal storage, that's the level of storage that you want. Like this volume is like if you want to do it an overground vessel, it will be taking the whole Vizag city actually for storing that level of hydrogen. So you cannot do that. You put it under the ground in a natural formation, and when you want to take it, you do it. So this is basically showing this. Even for this condition here, it shows you that case 3 is profitable compared to case 1 and case 2. So this is interesting. Then this shows you some interesting thing here. Like this shows you dynamically what is happening in terms of the cavern storage. So here you see the price is actually very low. So it is basically saying don't shut down the plant, produce hydrogen, store the hydrogen in that vessel, put it into the cavern. So this is happening during summer. And during winter, the optimizer says, well, this is the winter comes in and it is fluctuating. This tells you that those are winter months. Sometimes you produce, sometimes you don't. So then you take it from the cavern here. Notice that we are starting from 0 to 0. This is because we had an optimization constraint that basically saying where you start, you must finish there. So that I'm not drawing from out of nowhere. So that's why it's starting at 0 and ending at 0. Okay, but this is interesting that how it really happens over here. Now, this is the New York ISO. Again, New York is not so dominantly summer or winter. That's why there are two peaks here. So one is that you can clearly see this is also during summer and goes down, but then it is not very monotonically going down because it is not clear cut like a winter, because we do know during the fall time, sometimes the temperature will fluctuate for a couple of days or even a month, and it seems like, okay, it is not fully winter. You might still be able to produce some power. So this is what it is actually showing, but it takes care into account this all the dynamics in the LMP and makes the decision at every point. Okay. So switching gear, this is a new idea about decarbonization of distributed power production. So you might get confused, what is distributed power production? So I'm not sure about Vizag, but if you are from any other place, maybe in the big cities, the power do not go off as often. But all of us know about the load shedding, right? We basically say setting the load, sometimes the power will go off. But if I come and tell you that your power can never go off, period, never, not even for a second, unless this is like almost the end of the world or something like that. If that is the scenario that you want to have, you need a extremely tight control. So in general, that is the whole idea that people do it in the US. Normally, you will never see the power go out. The only time we have seen power goes out is like there is a massive snowfall, and then because of the snowfall, the snow kept accumulating there, and then it probably, some of these transmission systems, it actually collapsed because of the weight of the snow at the top of it. So very extreme weather conditions that you will see it. Under normal conditions, you will not see this. Or maybe there is a tornado or any kind of a big storm, and then it uproots some of the transmission lines, but it could be locally. Big cities, you will never get it. Like places like New York City is fed from 4 different sides. So one side get caught, other side will get in. This got cut, another side would get in. This got cut, another side. They have a 4 type of redundancy for any location in New York City, so that you never lose power. That's the whole idea there. That type of scenario is extremely difficult to maintain. You need a lot of mathematical power to do that. It's not the generation power, it's the mathematical power. You need to have that because you are always projecting and forecasting. You have to have the weather model. You say tomorrow what's the temperature is going to be, whether this will be windy, this location, how much power demand will be, how much the people will be cranking their AC, how much power load will be there, who are my generators in the system, how much nuclear is coming, how much wind is coming. So those optimization problems are solved together, and that is how they forecast for the next day. That's the scenario there. Out of the entire puzzle, there is one thing that is known as the distributed power plants. These are peaker plants. So what they do is that even after those meticulous planning, there are still some uncertainties. So what you do there is you have some idling turbines. They are just slowly running. They are not giving power to the network. The moment there is a cloud cover comes in front of the sun, those solars will go down immediately. Who will take the load instantaneously? The normal power plants, they cannot crank up their load so fast. So you need these guys who are distributed. They will instantaneously go. These are actually aeroderivative turbines. These are like aircraft turbines, like which you see aircraft engines. They are rapidly can actually give you the power. These are those type of engines actually. They immediately go there and they basically say, yep, we have you covered. So that's how you never see a dip actually, because those guys picks up. So they have actually many such peaker plant in each of these ISO. So these peaker plants, they normally run or either on natural gas or on diesel. Right? So now it is more on natural gas. These are single cycle or the simple cycle plant as opposed to combined cycle, natural gas combined cycle plants, because just like gas turbines, like that's how they have it. Like the Carnot cycle is not present there. The back end Carnot cycle is not there. So it's only the front end, okay? So question is, how do you do this? So here the idea is that you have electricity. Again, you produce hydrogen, you store it, and then you actually, whenever you need it, you get the hydrogen here. And then you have considered different tax scenario like 100%, and then we have a hydrogen injection limit, because right now many of these GE turbines that they are using it, both GE and Siemens are actually the big players in this domain. They can accommodate up to about 15 volume percentage hydrogen. So we constrain that actually to 15 volume percentage, okay? So there are different scenarios. So first is that you put a tax and then you say you must use hydrogen as 15%. So even under that scenario, it basically makes some money. It's not much, but it makes some money. Look into this interesting profile. This is too much thing, but I'm just only showing 300 hours here. This is more than 3,000 hours, but this is 300 hours. So if you notice here, you will notice that whenever the LMP actually goes down, like for example over here, that is the time when it is actually producing hydrogen. And then whenever that LMP actually goes up, the electricity price goes up over here, that time you see the gas turbine power goes up, that is actually it is firing the hydrogen. So the optimizer actually keep optimizing it. So most cases it is basically saying, okay, you produce here, fire here, produce here, fire here, produce here, fire here. So like that, and making that optimal decisions for the entire time. Another scenario is that you are free to decide. I'll put a tax on you, CO2 tax, but you put the hydrogen, do you want to fire it? It basically say, so this comes to the lower end that basically we put a lower limit here. It's basically saying, no, you should not buy an electrolyzer, you just pay for the tax. You make more money by paying for the tax rather than firing hydrogen. Then the next one is the CO2 tax. We say 0, there is no penalty, but you have a hydrogen, you must fire 15%. In that case, you will see that it actually has got a good bit of a power here, and then NPV is also high. And the reason here is that the plant is not losing money. This is simply telling you one interesting thing is that putting a tax to CO2 does not solve the problem. The plant will simply shut it down. It is just basically saying is if you tax me, what will actually happen is that I will either cut my throughput or eventually I will run out of business. That's what it's basically saying. So you have to give a solution and then you put a tax. In a case that even with a tax, it can come with a solution. So this is what the optimizer is saying. It's very interesting even in real life because they have no recourse. They cannot do anything with it, right? The other one is basically CO2 tax is 0 and again hydrogen 0 to 15. This is probably the most interesting one. Because we put a lower limit for the electrolyzer, it came to here, but you notice that hydrogen volume is 0. It's basically saying that I will buy the electrolyzer because you force me to buy, but I will not operate it. Because operating it, I'll make more money, I'll be losing more money. Why? Because the moment you operate it, the issue is that you have to pay for the storage vessel. And it is basically saying, instead of that, under this scenario, it is actually I'll making more money even without firing or storing it and just paying the carbon tax. So this is basically telling you that technology space is actually very important. Like you have to have a technology maturity for making such decisions. So these type of models really needs to be there with the central government or the federal government for making their policies. You cannot just make a policy saying from tomorrow you must do this because actually there is no option. The plan, given the current state of the technology, if these decisions are not optimally made, it actually make the business, they will run out of their business. So that is what basically it says. Okay, I'll be quickly changing the gear. So I'll just say the artificial intelligence and machine learning, there are a lot of opportunities here to show, but I'm just showing here only one of them as part of this, okay? So here, this is a work that which we have been doing with Technology Center Mongstad. This is a pilot plant in Norway. this is the world's largest CO2 capture pilot plant, right? And somewhere on the side of the black sea it sits, and it gets the flue gas from a nearby petroleum refinery. It's actually fluidized catalytic cracker combustion gas, actually, the regenerator gas. And it's very advanced, has got a lot of really nice features there. So one thing with Norway, and that's true for many of the Scandinavian countries, their emissions regulations is actually extremely strict. And they will basically, if your emission goes beyond some level, they will basically first shut you down. They will say, okay, you figure it out later on, but now you shut down, and once you figure out what the issue is, then you can restart it again. So that's how they actually operate it. So one of the issue with the solvent-based capture is that there are a lot of degradation product that shows up in the stack. So even in the ppm level, some of these emissions are not acceptable. So there, as I said, that air emission control is very stringent. However, so I'll show you what happens, like a lot of this mechanism that takes place in a amine-based capture system. We really do not understand it. Nobody really understands exactly what mechanism takes place. Extremely complicated mechanisms forms actually many components as part of those degradation products. Some of the products that people have already documented as part of a petroleum refinery, petrochemicals, where they have used amine forever, it actually produces more additional chemicals here. And petroleum refinery, because it did not have that level of regulations. But this is one of the challenging ones, okay? So what we did there was that we worked with them. This is a US Department of Energy project, and we wanted to work with them to say that, can we develop a machine learning model? So over the years, one of the projects which we have been looking into is that you are seeing a lot of work going in the space of deep neural network. So in sometimes it can be a mindless deep neural network, to be honest with you. I mean, like you would say, oh, I have got hundreds of layers there and I have got millions of variables. Fact is, you are overfitting it. You cannot use such models for prediction. These models are okay when you give the data and you will perfectly fit, but actually what it is fitting is a noise. It's not the true data. So that question is very important to answer, that this is the biggest danger of a data-driven model or artificial intelligence model there, that you may be very happy looking at the fit, but what you are fitting is actually the noise. So the idea was that, okay, can we come up with some clever structure which can lead to a lower number of parameters to be estimated, like you are seeing that what Dr. Palla was actually teaching you was that how to estimate the parameters for the isotherm model, because it is a good, well-known isotherm model, so the parameters are there. But now, if I actually give you, instead of a dual site, if I say, okay, I have got n number of sites, and you will have lots of parameters there. Any data you give, it will fit. But you use that model for predicting an unknown thing, you will see that it will fall apart. And this is the biggest thing there. So how you can develop a predictive model. So that was the whole idea, but without going into machine learning model, we did a lot of structure here and algorithm, but I will show you some of the results here quickly. Okay, I will show you, this is the standard objective function that you will see even in the machine learning literature that is actually used, or parameter regression that is used. Remember, this type of an objective function, when you minimize the squared error, this will monotonically go down as you increase the number of parameters. So if you have this objective function will go lower and lower and lower. Maybe it will only exponentially decrease after some time. So it will be a decaying exponential after some time, but it will monotonically keep decreasing, right? So you need something that should penalize you, that you are not decreasing much, but you are increasing the parameters quite a bit. So we also considered another objective function that actually considers the covariance estimate of these parameters. So we have a log likelihood function here, and the covariance estimate of these parameters also as a penalty. That tells you that, well, you are actually overdoing it or overfitting it actually. So that's what we do it here. I'll quickly show you some of the results here. You see these are extremely noisy. Look into the scale over here. These are ppm level, 1 ppm, 0.6 ppm, 1.5 ppm. So these are actually spectroscopic data. So these are actually infrared range spectroscopic data from which has been calibrated for giving you the true chemical. So that these are really newer generations instruments they just installed at TCM for monitoring this. So these are kind of almost like a first round of data that which we got. I don't think this measurement technology did exist before. Okay, so again, this is an ongoing project in progress. But what I would like to say is that we have been in the group also working quite a bit in terms of a hybrid modeling. So what we learned from chemical engineering, I personally believe that there is a lot of emphasis in terms of a data-driven model. That does not mean that we are throwing away all our fundamentals chemical engineering. Even you can try a reaction rate, RNAs type of a model. It has got only 2 parameters, A exponential minus E over RT. If I give you the data and you try to fit it with a data-driven model, you will see you will require hundreds of parameters to fit. But the true model is given by only 2 parameters, A and E. This is the power of the form of the equation. That is what, as chemical engineering fundamentals, we have developed over the years, that what should be the equations. We are not giving out those fundamental knowledge that has been acquired over years. But the data-driven modeling brings a lot of strength. So idea is you can hybridize it. So use data-driven when needed and use first principle or our fundamental chemical engineering models together. So synergistically use it, exploit their strength, right? So that is what we are doing. So these emission models, yes, we are doing it, but these models can predict something. I understand this can be wrong. So we are actually also looking into physics constraint network for this type of models to basically saying, can the physics tell me that this cannot overshoot by this much? Can the derivative be constant? Can the actual value be constant? So this is an ongoing work here, but hybridizing is one of the good things. So in the concluding remarks, I would like to say that decarbonization is actually really required for centralized and decentralized power production, but the decarbonization strategies will be different and it will expected to vary from region to region. The solution for this part of India is not expected to be the same that if you're looking into northern part of India or the eastern part of India or western part of India, because the climates are different, the temperature projection is different, how the system cycles is actually completely different. So you must be looking into it optimally for each one of them. The other thing is that what we found out, this seasonal hydrogen storage, it seems like it might work. And this is something right now, and I think that project is still going on. There is a Mitsubishi plant coming up in Salt Lake City, Utah, in the United States, where basically the entire city of entire Salt Lake City, the idea is that it will be all powered by hydrogen, and the storage is actually over there. That salt cavern is around the Salt Lake City itself. So this is actually an ongoing work that is going there, and this model says this is feasible. You can do it. You just need a massive amount of storage, and this type of structures will give you the possibility. The other thing is the reward or the penalty. There are 2 approaches all over the world. It could be in form of a penalty, which I said is a tax. It could be in form of a reward, and I discussed that as part of our workshop. The reward is in terms of a tax break. So I tax you is a penalty, but I can also put it, instead of a penalty, I can give you a reward. I can basically say, whenever you are filling your tax return, you don't need to pay me this much of amount. You just take it from here. So you deduct from your tax return. So those are incentives. So both approaches can actually work, but those are essential, but that cannot be applied just arbitrarily. If you do it, it will lead to shutdown of the plant. So you basically run out of business. I also wanted to mention that AIML has got a lot of opportunities for sustainability. We have been looking into this quite a bit of use of AIML synergistically with chemical engineering. It is not like it's completely separate as a data-driven model, but how can the strength of both sides be mixed together to give a powerful tool that takes advantage of both sides of the world. Finally, I will be actually shamelessly advertise a little bit for the university. I will say we have a lot of opportunities at the university for the students, especially who might be interested in graduate studies. Remember, we as a professors, we always like students to come to the graduate studies. We want everybody to come to be PhD. Really, this is the most exciting thing for us, and that is why we are here. We love our profession. We want all of you to come to PhD studies. So I will say that we have multiple area. We have a biotechnology. We work extensively with our health sciences. Our medical campus is actually on the campus itself. It's part of our university itself. We also work extensively with the energy technologies, materials, and process and energy systems engineering. When you say energy technology, this is all catalyst and those type of things. And then you can visit our website for taking more of this, looking more into all our professors' profiles. Everybody's profile is all there. You can see what are the areas that which we work on. And I'm right now our graduate admission coordinator. So if you have any questions, you can send it to me, or if you send it to that email, it comes to me actually, so I can answer any questions. Or you can ask me here actually about admission process or any other thing. Like even if you are asking it in general for any US universities, I'll be happy to share that what are the things that are needed. We are located about 3 hours drive from Washington, DC, and 1 hour drive from Pittsburgh, and it's a typical US university town. We have about, generally during the summer when the students go, we have like almost like an empty town, like 30,000 students, but we have got a lot of pretty much anything that you get here in any big cities, you will have more than that anywhere. Everything you will get there locally. There is no issue in terms of getting any of the facilities there. So everything is actually there. And we get all admitted student get a research assistant position. And our engineering really, for teaching assistant, we do not take anybody. We pay about $31,000 per annum. We feel that this is generally more than sufficient for any graduate students. You can travel easily, at least once in a year to India, and all students like buy their car and everything. So usually that's not a problem in terms of money, we believe. And we generally are always open for qualified graduate student and postdoctoral fellows. We have all those things. And then finally, I will like to acknowledge the students who actually worked here: Stephen Summits, Nishant Giridhar, Ole Jienka, and Dr. Imdadul Haq and Dr. Angan Mukherjee. All of them actually contributed to the work that I presented. All the work that I presented, these were all came from US Department of Energy grants, and these are the grants that I gratefully acknowledge. And any questions, please? You can have a technical or a non-technical questions. Anything is fine. Could be for the first part where I talk technical, or it could be non-technical, please.
So those caverns you were talking about, are they man-made or natural
No, man-made. So there are actually salt formation. So many places under the ground, there is a salt formation. So what they do is that I really do not know exactly what chemical they use, but what they do is that those salts, so they have a structure at the top of it, again by nature, that will hold the hydrogen tight. It will not let the hydrogen leak through it. But then below that, you have the salt. And so what they do is they will actually almost like think about it, you put water or something, it's not water, they use some other chemical, and then they make this portion hollow and then empty out the salt from there. So those are that's why they are known as the salt caverns. So those are the massive size salt caverns. When I was saying this is an older technology, actually air storage is, you have probably seen that lot of work in terms of the air storage in that area. That is also one of the energy storage people are actually doing there. But for the air, there could be other formation that can be considered. There are a lot of hard rock structure, right, that can actually be utilized. Like for example, you have a lot of mountains over here. So if you study the rock structure below that, there could be formation that will actually hold it tight. But hydrogen is, because of the safety concern, there are these formations which are actually nature made, and you just empty it out. This works such a way that it will not let hydrogen permeate, because it became very smallest molecules, it will actually go through any of the leakages. So CO2 you can store in many places, air you can store in many places, but hydrogen you have to be very careful. That number they actually gave us, because that 300 million, this is because Lindy is actually in that space of hydrogen, so we kind of based on the discussion with them.
So in these caverns, hydrogen are being stored in a pure form or in terms of halides or some other?
No, pure form, it's gaseous form. Yeah, this can actually withstand, I have to exactly remember, but it's actually a couple of thousand bar actually. The rock structure will hold it. Yeah, I think there was a question.
The hydrogen is stored in cavern or high pressure.
Right.
1000 bar.
Right. Yeah. They have a internal compressor also. That as part of the cavern that they do actually. During the morning and day temperature cycling, if the pressure goes up and down, they actually can, those internal compressor kicks in and then it keeps it under a storage pressure actually. It's interesting how they do it, but this is practical and people are doing it.
So it is recyclable.
Yeah. So all the hydrogen you store, you actually can take it out and you fire it, and then whenever you have hydrogen, you push it into the cavern there. Yeah.
So in terms of the commercial, its cost effectiveness, it's storing hydrogen at high pressure at higher bars, or say storing the energy in terms of advanced chemistry cells, or say maybe pump storage. So as per the Indian context, hydrogen has not become yet viable, but storing the energy in the pump storage or higher chemistry cells is cost effective. In fact, I was just reading some of the articles few days back. Means the cost of power in USA is one of the highest, if I'm not wrong. So isn't it also not being explored in terms of energy storage or pump storage, how it can be stored for similar radiations?
So the idea here is the question that we have to think about how much you are storing. So when you form it in terms of the chemicals like halides and other forms, the biggest issue that comes is about the energy density. As we all know that for hydrogen storage, hydrogen, while it has got a very high energy density, one of the highest energy density in terms of the mass, but in terms of the volume, it is actually one of the lowest. So the only way you can get really high energy density is by storing it at a very high pressure. And these type of systems actually let you store at very high pressure a massive amount of volume that can feed. That is the problem with this. Like if you're saying, okay, I'll form it in form of a halide and I want to power my house with that, it may be possible. But if I say, no, everybody in the Vizag will be all powered by hydrogen, everybody in Mumbai will be powered by hydrogen, then we are talking about a massive amount of hydrogen. I think that's the scale, that is where these type of things are coming into picture. Right, and in terms of the price, I'm not sure about the price of the electricity in India right now, but I will tell you that working many years as part of petroleum industry, I have always been amazed that US actually the gasoline price is much, much lower than India. It's completely other way around because all plants are actually optimized to the dime actually. You just cannot move any of it. So you go to any of the plant, each operation conditions is actually extremely optimized. People spend many, many years to say, this should be the temperature, this should be the flow rate, this should be the thing, and all of those conditions. This should be the yield percentage, which I did not feel it that way. I worked for 10 years as part of Indian Oil Corporations Limited, and I did not feel it that I could tell that I just cannot make any more profit there. So it's difficult to say because they pay more money for human. They will pay you per hour more money, but they will not let you waste. So all operating conditions, there are a lot of mathematical programs actually running behind the scene and developed as part of the plant operating conditions that they keep optimizing all the time. Any other questions?
Yeah, I have one question about the application of AI and ML for a predictive model for say any PSA or VSA application.
Yeah.
What is the minimum number of data point we need to have to actually be very confident about the ability of the model to perform? Of the surrogate model, of course. Because from what I know, people have been publishing based on only 30, 40 experiments. But from what I read, it seems that the more the data you have, more accurate it would be, or more reliable.
I wish I could answer your question. This is the answer I have been looking for, and in the current research literature, nobody knows. If the system is linear, I can give you the answer. Nobody knows this for the nonlinear systems. How much data is enough for it? So there is something called a richness of the data, which you probably have heard. This thing has not been defined. So for a linear system, you tell me that this is a linear system. I can exactly tell you how much data you need. And this has been documented as part of all our system identification literature. Like if you look into the controls, Professor Lung's book, System Identification Theory for the User. If you read that book, this has got a significant coverage. It's actually from the covariant structure itself, you can tell it that how many data points you need. So if I have got n first order differential equations that I'll have, if there is no noise present there, actually n number of data points are enough for you to give that, right, in absence of noise. Otherwise, you have to give the noise characteristic. This is not known or obtained. I have actually personally thought through it for many years. I have no solutions. If I do that, this will be a seminal paper. Anybody has it, it will be a seminal paper. Nonlinear system, there is no general answer to tell you how much data is good enough. Even if you collect, like instead of 40, you collect 60 data points, and you say, oh, this is good enough, yeah, but you did not actually sample one of the nonlinear systems. And that is why you never could actually see it. So I always try to draw this and try to, well, I cannot draw it here, okay. So that's okay. So if you have a nonlinearity, the problem of the nonlinearity is that you sample from one space. and looking at the samples from the space and you sample in the neighborhood of it, it shows you have a very good match. But the problem is there is another space that exists and you never sampled it. So how do you know if you, so this is almost like not knowing what you don't know. So if I do not know what I do not know, how can I say that I know everything, right? That's the issue with the nonlinear system. But a linear systems, because the behavior is predictive, then once you sample it, you know, okay, this is, even though I sample it here, this is going to behave like this. That's the difference, actually, yeah. Okay, any other question? Okay. Very good. Maybe from the students, any questions for you guys?
Another question.
Uh-huh.
So in the current scenario in the US, means based on the changing government or the changing government policy, so now the rather focus has been shifted from renewable to conventional, maybe coal, petroleum based, even nuclear based. So how this context is changing the kind of carbon capture and treatment, because as you were giving the example of California, California is extremely energy intensive because of all the data centers and tech hubs are big, and they are investing highly into nuclear power. So how it is changing the energy scenario as we have defined?
I will probably refrain from getting into any political thing here, but one thing I would like to make the comment here is that it is being produced from renewables because it's not because the renewables are doing it because of the pressure from the federal government. It is because of the money. It is because it is cheaper for them to produce from the renewables. Remember what I was actually discussing before. Like for example, just hypothetically consider your case. Like if I put a, like you go to travel to many parts of California, you will see houses, actually everybody has got their roof covered with solar panels. Say I give you that solar panel free, and that solar panel lasts you for 25 years. Why do you not produce the power? Because it is automatic, right? Sun comes every morning and it will give you the power. And the capital expense has already been paid for. So it's the cheapest source of power because you are not spending any money at all. So these companies are producing using the solar or wind because it is cheaper to do so. It's not because it's because of the CO2 capture or CO2 or anything. So I don't think that scenario is going to change. The question is that whether the rate of progression of CO2 capture project, how it will change, only time will tell. But I don't think the power production as it exists today, that is going to change. That portfolio is going to change because this is not because of this carbon tax or incentive. This is because it is cheaper that way to do so. Everywhere, like even in India actually. If this entire roof here, actually all covered, now you have almost 30% efficiency for solar panels. If all these roofs here are covered with solar, India has got so less power demand. You can actually produce everything by renewables. We have got sun all the time actually. But the first thing is the capital expense. Somebody has to cover that capital expense or have the incentive like in terms of tax or whatever. Once it is done, it will automatically keep producing it. Okay, any other questions? I want to get one question from the students at least. Please, all of you are here. Any question is a good question, no worries.
So when we're talking about the node with the amine solvent issue, so basically there's a study where a new company has come with an idea where rather than capturing carbon dioxide using amine solvents, they're actually breaking it down into carbon with pure elemental carbon, which they found was for them was more profitable. So like just want to ask your thoughts about how you're going to take your research forward, since they have found this new way where they're producing elemental carbon which they're finding more profitable than using amine solvents to capture the carbon dioxide.
Right, so the issue is all about thermodynamics. So remember how you produce CO2 and why we produce CO2. So first is we produce CO2 because C plus O2 in some form. So it could be natural gas like CH4 plus O2 gave you, or some hydrocarbon, or the coal like fixed carbon, or the volatile matter in the coal that reacted with oxygen to give you the energy. CO2 is actually one of the most stable molecules. So when you actually try to decompose it, or we do pyrolysis of it and try to decompose it, so thermodynamically, because nothing is 100% efficient, so whatever energy you got from it, you will have to put more energy to break it. So energetically, it makes no sense. When it makes sense, now if I come to you and I say, well, I have got free energy, do you want to utilize it? Yes, then there are question come is that if somebody has a free energy, what is the best usage of it? So that's one thing. But with that said, I would like to take it to a different point, and this is because one of the project that I have, I will tell you this, from the coal, one thing which we are trying to do here is that the coal has got a lot of carbon, and coal is the biggest issue. So any country that burns coal is really producing a lot of greenhouse gases. That's the issue. That's the biggest issue. If you switch to natural gas, immediately it will go down, right? But now the question is that is it possible from the coal that you just take the carbon out and then remaining hydrogen and other things that you utilize it? Yeah, if it depends upon what type of coal you have and all of that. But one thing which we are trying to do is that if you can break it to get even like CH4, like methane, you can pyrolyze it and get it into carbon plus hydrogen. And that carbon we are looking for using in the lithium-ion batteries, actually. The anode of the lithium-ion batteries, which we are using in the car and all the cell phones and all of that, the standard anode material is a carbon. Right now, those carbons are produced generally by two methods. One is coke calcination process, like petroleum coke, and they are calcining it and produce it. That is costlier coke. Like you can produce needle coke and that type of coke. Another type of coke are actually mined. So that is one of the best quality coke that are mined, which is mostly comes out of China. And now China actually shut down a lot of their mines from where those graphitic carbon were taking out. So there is a worldwide lot of demand for those type of a carbon. So that's definitely a new thought that helps you both ways. You make money by selling is at a graphitic carbon, like for batteries, and then you also decarbonize it by producing hydrogen. Yeah, and we are trying to do is by using microwave energy actually, so that you are not heating it up. Otherwise, this pyrolysis will take place like around 800 to 1000 degrees centigrade temperature. The moment you take it to such a high temperature, it's not profitable anymore. So we're trying to do it at like a room temperature or 100 degree temperature by directly using a microwave catalytic process that will directly decompose it. Okay, any other question? Okay, if not, I'll be hanging out here. If anybody has any other question, let me know. Okay, thanks for your time.
Thank you, Devanshu, for the wonderful talk. So tomorrow morning we will meet for the next lecture, okay, around at 10 a.m.